Let's see. Test, can you hear me? Works? Perfect. All right, thank you.
Okay, so good morning, everyone. Welcome to this last day, which is dedicated to control, closures, and perspectives. We will start with application to aerodynamic and multidisciplinary optimization, and the first lecture is given by Professor Kurtz. Please.
Thanks, Miguel. Good morning, everybody. This talk also would have fitted the session yesterday, I believe. This talk, you don't expect a lot of equations. I'm really trying to show you some applications. But the talks that you've seen throughout the week, I think, are a good preparation for this talk. So I will not have to repeat what you've seen in previous days. All right, so this is a talk about reduced auto modeling activities that we perform at the German Aerospace Center. This is not my work. This is work that my colleagues have done, and I'm acknowledging them here. Just before I start, I'm from the German Aerospace Center. We are the National Research Center for Aerodynamics and Space. Bernd.
Maybe you would not be here if it were your work.
That's right. We are also the largest project management agency in Germany, and we are the German Space Agency. Currently, we have about 9,000 employees, and we're still growing to about 50 institutes throughout Germany. And I'm from the Institute of Aerodynamics and Flow Technology, and there I'm the department head for the CASE Center. CASE stands for Center for Computer Applications in Aerospace Science and Engineering, where we perform, where we develop numerical methods and apply them to different challenging aerospace problems, including aeroacoustics and aerodynamics. One of my groups is dealing with surrogate modeling, reduced order modeling, uncertainty quantification, robust design, and MDO. And we're also more and more using machine learning methods. When this course was first set up, I think it was more focusing on the reduced order modeling aspects, which my talk is about, but I'm also trying to touch upon the machine learning part, and I think the course has evolved in that direction a little bit, so I hope this suits the idea of this lecture series. All right, so what I'm going to talk about is, first of all, a small motivation, why we are looking at these methods. And I will talk about what we call the virtual aircraft use case, which is challenging. I will try to connect these reduced order modeling methods to the principles of machine learning, and show you some of the methods and how I classify them, before then delving into a quick introduction to our reduced order modeling approach. And the main focus really will be on applications, on the one hand for steady flow problems, and on the other hand for unsteady flow problems. If I have time, and this we will see, I will also talk about data fusion applications, which I think is really interesting to combine the best of two worlds, be it flight test data and numerical data, or experimental data from the wind tunnel, or all three of them. All right, what is the motivation in terms of the virtual aircraft use case? If you want to design and certify an aircraft, you need lots of aerodynamic data, right? And this data is needed throughout the entire flight envelope of the aircraft, right? So at cruise, where you're sipping your coffee, things are not very exciting, and this is we can take good care of this with today's methods. However, you have to prove to the authorities that the aircraft doesn't break throughout the entire flight envelope, and you encounter much more challenging flow phenomena, be it separation, buffeting, flutter, you name it, and all of this has to be taken care of, and in particular this has to be taken care of also in terms of the structural sizing of the aircraft structure, right? The aircraft shouldn't break during flight. To do that, you need a lot of dynamic data, you need integral coefficients, you need distributed quantities such as pressure or shear stress distributions, both steady and unsteady. And all of this is coupled, right? This is a coupled system. I'm dealing with the aerodynamic part, but we're coupling to the mass model, we're coupling to the flight control system, and in particular, we're coupling with the structural model. And there's some estimates to compute all of the different load cases and the data you need for performance evaluation of the aircraft and for handling qualities may sum up to the order of between 1 and 10 million different cases which you have to compute, both steady and unsteady, stemming from different flight conditions, right, different mass configurations, different maneuvers and gusts. So what people call turbulence, or what people call air pockets. In truth, we call this gusts. And different control laws that you have to consider. So there's a large number of cases which you have to compute for each and every configuration, right? So if the design is evolving during the design process, you have to repeat these computations several times. And to tackle all of these cases with high fidelity CFD or CFD CSM is on the horizon, but it's not feasible. And that's, I think, the motivation for us to look into faster methods on the one hand, so things like double asset methods, but on the other hand, also trying to build reduced order models out of high fidelity data. And the challenge is to compute as little data as needed as possible. All right, and the goal is really then to predict all of these aerodynamic quantities based on parametrically generated high fidelity data stemming from CFD or CFD CSM computations. Of course, hoping that these models which we are trying to build have lower evaluation time and lower memory storage than the original CFD. And the quantities of interest here are, again, pressure and shear stress distributions over the aircraft surface in particular, but we also may be interested in volume quantities, so the primitive variables which we're also dealing with in our CFD code, be it pressure, velocities, or temperatures. What parameters are we interested in? On the one hand, we are of course interested in flow parameters such as the Mach number, the angle of attack, and this is shown here, different angles of attack for a profile. But we're also dealing with different geometries, right? In the design, the geometry is evolving, and we need to parameterize this geometry. And ideally, we have a model for all of these parametric changes, which is really challenging. So the typical process is to start defining a design of experiment, to vary these parameters in a systematic way, to compute these snapshots. I'm sure you've talked about snapshots during this week, which are typically full order solutions to the high fidelity problem. Then the challenge is to build a reduced order model, whatever that is, which is a low-dimensional description of the dynamics of the fluid flow around the aircraft, which of course has a restricted range of validity, right? Thus we have to accept we are talking about a prediction in terms of an approximation of the full order system. And this then can be used to predict at different parameters, ideally of course parameters that you haven't used to train the model. In this case, an in-between angle of attack, for example. And what we're really aiming for here is we're not always interested in really saving computational time. It may even be that we're spending more CPU hours than by just computing everything with high-fidelity CFD. We're trying to take advantage of the offline and online phase, as we call it, right? So you may be able to start computing data parametrically on a big HPC cluster offline long before you actually know what you want to compute. Sounds strange, but this is called, in the industry, that's called an out-of-cycle design, right? You're kind of collecting data, you're trying to build up your database when not yet knowing what you actually want to design, right? And once your objective function, for example, becomes more clear, you just have to cast the data into that problem formulation, and you can also reuse the data in case the objective function of your design is changing, right? That's one of the ideas. This we do offline, so have the data ready. Once we want to quickly evaluate the reduced order model during design in an online phase, and ideally this can be done on a desktop or in flight on the flight computer, on the computer that you take into the aircraft to make self-learning aerodynamic models. And here's an example of a real-time prediction, right? This is not very fancy, it's only 2D airfoil, but this is the grid that you see, so it's a RANS computation, including viscous effects and transonic effects, and we're changing different parameters. We're also integrating the aerodynamic coefficients online in real time here, right? So this is not too difficult, and in 2D, in 3D it's more difficult to get to real-time capability, but I think this is quite impressive because we're also predicting the geometry deformations and the grid deformations simultaneously. All right. What is the connection to machine learning and the machine learning principles and reduced order modeling, right? So this is my classification. This may not be agreed upon with everybody here. So a lot of times people say, we talk about artificial intelligence. And when we talk about artificial intelligence, DLR, we typically mean machine learning. There are, of course, other branches like robotics, which we're also dealing with, but here I'm talking about machine learning. And I think there is two main categories of interest for us. There is supervised machine learning, so predictive models, right, based on input and output relations. And there's unsupervised learning, which I classify as an internal representation only using inputs. And there are different techniques, classification, regression, model selection, clustering, and in particular, which I'm interested in, dimensionality reduction. And these are the methods that we use. So the simplest one, which we have always used for a long time, is a classification method, which is called nearest neighbor. And I still think it's funny that one of the most successful machine learning algorithms that Netflix is using is nearest neighbor, right? We are also interested very much in regression models, right? So predicting values, and methods we use are Gaussian process models. We're using Bayesian regression, very powerful tool. Different regression techniques, ridge, lasso, kernelized regression. And more recently, we're using different artificial neural networks, and I will touch upon that later, and support vector regression. We're combining this with dimensional reduction methods, in particular PUD, which you've heard about here. We're not dealing with DMD yet. I'm interested in that. We are looking at isomaps, so nonlinear dimensional reduction methods. We are doing manifold learning and interpolation. We're using autoencoders and lowering approximation and hyperreduction. If you combine all this with clustering, then you arrive at methods like clustered PUD. ISOMAP is also a clustering technique. At the same time, we're using K-means and spectral clustering and affinity propagation algorithms. To train all these different parameters, which then arise in selecting these different models and methods, we're also using model selection algorithms such as grid search, which is very expensive. Of course, classical things like cross-validation and hyperparameter tuning. Also, again, one of the most important features of what Google is doing is to efficiently train hyperparameters, right? And we're doing adaptive sampling. And again, you may argue about this classification, but this is my classification, and just to give you an overview of the different methods we're using, and which I think are connected at least to what people today call artificial intelligence. All right, all of these methods are implemented in our own toolbox, and this is a modular object-oriented Python package for rapidly predicting lots of data based on high-fidelity CFD. The methods, some of the key features are that we can do design of experiments, we can do adaptive sampling, we do surrogate modeling, so classical surrogate modeling, but also in artificial neural networks where appropriate. Very interesting is variable fidelity modeling, right? Having data of different quality and of different origin, of different sources. To combine that, may it be numerical data of different origin, or may it be measured and numerical data. Very important for today's talk is dimensionality reduction and reduced order modeling. And all of these methods are part of our flow simulator environment, which is a data backbone, so to speak, to exchange data between different plugins. And I will talk today about our flow solver plugin, the Tau code, which is the RANS code, and the Smarty plugin, which is the method or the toolbox to deal with reduced order modeling and machine learning techniques. What is interesting is that due to the fact that we have the simulation core, which is running in parallel, we have also parallelized our machine learning and reduced order modeling software where necessary. For example, the PUD part is parallelized and the residual evaluation, which we'll talk about, is parallelized. The code is partially differentiated, which is nice if you do optimization. We're using, of course, established libraries like MKL. We have interface to scikit-learn, very powerful, and of course, TensorFlow is being used for artificial neural networks. We are currently working on the GPU version. A lot of these methods lend themselves to running them on the GPU, and you can do very powerful things on an aircraft in flight if you take a GPU with you. And we also have standalone versions and use case specific adaptations. Applications that we have used this toolbox for are related to optimization, so surrogate-based optimization and uncertainty quantification, which together enable you to do robust design or inverse design. Today I'm going to talk about mainly two things. If I have time, fusing measured data and CFD data. The next two talks will be related to data-driven determinism modeling, so I will probably not talk about that, only if I have time. I will more talk about how to rapidly produce dynamic data for the virtual aircraft use case that I introduced you to. And I will not talk today about other important things like optimal sensor placement, right? So using the snapshots you have to derive a modal basis and then find optimal sensor locations where you apply greedy algorithms on the modes. I will not talk about wind tunnel corrections, which is very exciting, again, combining two worlds, measurements and CFD. But all of this is, of course, related to what we call virtual flight testing. You're, of course, trying to fly the aircraft in the computer. All right. Again, a second classification, now talking about reduced order models in particular. I will show you steady ROM applications and unsteady ROM applications. And I've classified the steady ROMs into non-physics-based or non-intrusive reduced order models. Right there, we're using dimensionality reduction methods together with interpolators or regression models, or with artificial neural networks, and I'm going to talk about that a lot today. I'm not going to talk about manifold interpolation, which is very exciting, but probably the time is too short to talk about this. And I will talk about physics-based intrusive models. I'm not talking about Guerrierian models, but I will talk about our alternative approach, which is based on residual minimization. In terms of unsteady ROMs, we have, again, non-physics-based ROMs. System identification tools are being used, interpolators and artificial neural networks. Not today's topics. I will focus on my favorite topic, which is physics-based, unsteady reduced order models, where we use unsteady residual minimization, and very exciting hyper-reduction methods based on the DIME method and the MPE, which all of you know, but to apply this to a real large test case, I think is what I want to show here, because that's also posing a challenge in itself. The most logical approach in reduced order modeling is to apply Gaulosian projection to linear systems, and we also have a reduced order model of our linear frequency domain solver, which I'm not going to show you today. Also, it's of course interesting to combine this with manifold interpolation. Just in case you're interested, these tools are already in the industry, right? So I think we're doing a lot of interesting research here all together. And industry is really interested in applying this because they have really challenging problems ahead of them where we can help. All right, so in a nutshell, how do we construct reduced order models? We're first doing a step which is called dimensionality reduction. And I will here focus on PUD, which you've learned about before, so this is just repetition. We're computing snapshots with the CFD code for different parameters, input parameters x, and get the snapshots y. We built a snapshot matrix, capital Y, and then the objective is to find a low-dimensional subspace that best approximates the snapshots. And this is sometimes pictured like this, right? You have a cloud of data points, you're trying to find principal components. Practically, this looks like this. You have your snapshot matrix stemming from different CFD computations, so n different computations. You're applying an SVD or an EVT to this, and you're, of course, typically trying to exploit certain features to reduce the problem, the computation time for the problem, and then you arrive at the PUD modes, the singular values, and the right singular values. And this is, of course, then giving you what is called the pod modes, and I've just pictured some of them here, and this is also in some cases they are lending themselves also to some physical interpretation. It's not always easy, and I think you've talked about this during the week, but it's not always that easy to interpret what you're actually seeing there. Here we are, of course, seeing different shock locations, and this is one of the drawbacks of PUD, right? We're basically getting, in transonic flows, we're getting different modes for different discrete shock locations, which you have to try to combine to find a new approximate solution, and that's one of the drawbacks. So every snapshot that you computed can, again, of course, be represented by the PUD basis in such a manner, right? You have pod coefficients A, you're combining them with the pod modes, and you can do that, of course, for all the different pod modes. And then, of course, the obvious idea is to try to find models, be it interpolation models, regression models, or whatever, to predict the pod coefficients, to then use the given pod modes to arrive at a new prediction. And that's what we show here. The easiest way is to just interpolate for these coefficients A, and then use a surrogate model, and for an unknown input parameter set x star, you're trying to make a prediction y hat by plugging this x star in your interpolator, and then you get new coefficients A, which you can then combine with your, or multiply with your pod basis modes to arrive at a prediction y hat. I'm sure you have talked about truncation before, right? So of course, typically the idea is to also truncate the modal basis. It's not always clear how to truncate it, but there's some heuristica to do that. And after this really brief and short introduction to the approach, I want to delve into applications, which is the main focus here. And I'm first talking about ROMs for steady flow problems. So in a nutshell, what we're doing is we have different parameters, be it Mach number and angle of attack. We define some training points very systematically using different methods like latent hypercube sampling, optimized latent hypercube, and different methods. Compute our training data with a CFD code to arrive at different snapshots. And then we apply the dimensionality reduction step, and I've just shown you PUD, but we're also using ISOMAP and autoencoders to perform this step, to then try to make predictions for the PUD coefficients or for the weighting of the ISOMAP vectors, or we're using residual minimization in the PUD subspace or in the ISOMAP subspace, or we combine these different approaches to find the model coefficients to predict then a flow solution on the surface or the volume, the full volume solution at an untried flow condition, of course. Here's an example of where we combine this idea with machine learning techniques on top, right? So here the idea was to look at a full aircraft configuration where we have computed high-fidelity CFD snapshots for 4 different design parameters. So the aircraft is changing geometrically, but we also have 5 different flight parameters, so flow condition parameters like Mach number, angle of attack, angle of side slip. And using a compressible inviscid flow solver, we computed together with Airbus close to 8,000 different snapshots. And each snapshot on the surface corresponds to 10,000 grid points, right? So here we have the solution at 10,000 different grid points. And the first idea that we had together with Airbus 10 years ago was to build a surrogate model for every grid point. May not be a clever idea, but this is what we tried. And this is a nice test case for evaluating machine learning algorithms. And the idea was then to build 10,000 individual Gaussian process models. And it turned out to be infeasible to do that because you have to tune the hyperparameters of these models you have to tune the hyperparameters for 10,000 different models. Just infeasible. Also, we already have a very efficient Gaussian process implementation where we have the compute-intensive part in Cython, right, for different correlation kernels. However, this was still not efficient enough, and instead we also went to the GPU, still didn't help. So instead, what we did is we looked at clustering, right? So having the different flow solutions at all the different grid points, we were looking for similarities in the flow solutions on the surface. And to cluster the surface points, to reduce the cost of hyperparameter optimization, we looked at spectral clustering methods and affinity propagation algorithms. And then what is interesting is to see that this even physically makes sense and you can interpret what's happening. So if you choose 3 clusters and just apply these dumb machine learning algorithms to the data, you find these 3 clusters, right? And this, to the anemonicist, this makes sense. You seem to find a cluster on the wing and which is partly extending to the fuselage, right? Which is the part of interaction between the wing and the fuselage. There seems to be a fuselage cluster, and there seems to be probably something on the engine. So this can be interpreted, right? So this is great. When you go to 10 clusters, well, there's still some features that the fuselage seems to be very insensitive or very connected in terms of the data. All makes sense. Going to 300 clusters, as we did in the end, cannot be easily interpreted anymore. And that's, I think, this is the power of machine learning, right? You're throwing data at the methods, and to some extent you get insight and you can still understand what's happening. But if you go to very large data, as a human, you are just impossible to find correlations, right? And this, I think, is the strength of these methods. There are skeptics to just believe in these methods, but I think I was very impressed by MIT colleagues who came up with new antibiotics, right? And given the current epidemia or pandemia that we're facing, I think finding new vaccines, new antibiotics with machine learning is great. This is helping humanity. And then I'm not questioning what's happening there. Okay, this is just an example of where we're applying these clustering techniques, and in the end, it turned out to take 380 clusters was the best choice here. And this is just showing you here the wing, the solution, the surface pressure distribution on the wing for 3 different approaches. We have the referenced full order model in red in terms of the pressure distributions at 4 different section cuts here through the wing, from top to bottom, so the outer wing to the inner wing. And we're comparing this reference solution in red with classic kriging that I just introduced you to, and we're comparing that with PUD with interpolation, so where we really build one model at every grid point, so 10,000 different models. And the first thing we see is that the 2 different reuse order models, which are shown here in green and blue, seem to give very similar solutions. There's a small problem here on the lower surface, so this line here is connected to the lower surface of the wing, and this is basically where the clusters meet, right? There is something missing in terms of boundary condition or an interface condition between the different clusters. Otherwise, this looks pretty good, and we're saving lots of computational time. However, and that's the main drawback of PUD here, the real shock location, which is shown here in red, and which is it's a very strong shock, very far aft on the wing, as you can see here, is not being predicted by any of these models, right? So that's not that good, right? So what's happening there? So let's look into this here, and let's see what remedies we have for this problem. And one of the remedies is, we believe, for example, ISOMAP. It's a method which was first, I think, published in Nature, and it's stemming from the image processing community, right? So they were interested in, in face recognition, you have very sharp contrast. You may have very sharp contrast in pictures, and this is kind of how you identify different people. And this is very similar to finding shock waves in a flow solution, right? And we thought, okay, this may work here as well. And so what you do is, in a nutshell, you're computing solutions of the full order model in your parametric space, be it angle of attack and Mach number, for example, in our case with the tau code. And then you can, these solutions lie on a manifold in some solution space, right? So this is the solution space here, and you can see the solution manifold here. This is the so-called Swiss roll example, just to illustrate things. And every point on this cloud is one CFD solution, one snapshot, right? And what is interesting is, let's take a look at this flow solution and this flow solution. If you are computing Euclidean distance between these solutions, this would be following this path here, right? Which is, of course, not lying on the solution manifold. However, if you're taking geodetic distances, which you can compute, then you are able to follow this, to follow the solution manifold and how it evolves. And this you can take advantage of with ISOMAP to then find a low-dimensional embedding of all of the snapshots, in which you can then, oops, I have to progress here, in which you can then interpolate, right? So you kind of try and connect your input parameters to the no-dimensional embedding of this data. And once you've found that, you can then make a prediction for a new point in the space and do a backmapping back to the full order solution space. And this is called a nonlinear dimensionality reduction method. And what's happening here, how does it work? We've applied this to, again, a wing test case. This is, I believe, the LAN wing, and this is Euler computations, inviscid computations. We've performed altogether 25 computations for changes in Mach number and angle of attack, more or less random DOE. And the idea was then to predict for this point here, shown in red. And on the one hand, we used all of the black samples, all of the black data snapshots, all 25, and build a POD-based reduced order model. And on the other hand, we try to use ISOMAP to find the 7 nearest neighbor on the solution manifold, right? And use these for the prediction. And the first thing that is interesting to see here is that the nearest neighbors that were selected by ISOMAP are not the nearest neighbors in the Mach alpha space, but the nearest neighbors on the solution manifold. And again, to the anatomicist, this seems to make sense, right? They know that it's not the flow physics evolve nonlinear in the Mach alpha space. So you can. I wouldn't have guessed which ones to take, but kind of what you see afterwards seems to make sense. And what is also interesting is that when using these 7 snapshots, they are much more related with the solution you want to look for than, for example, the snapshot down here. Right? This snapshot down here has nothing to do with the prediction here. And this is also what the method tells you automatically, to not include data which is not relevant for your prediction, because it completely messes up your prediction. All right, so we have done this prediction here based on these 2 methods, and we're combining POD and ISOMAP with interpolation first, so POD interpolation of the pod coefficients here, and weighting of the ISOMAP snapshots, the selected snapshots, to make predictions. And here I'm showing the surface prediction, but it's more interesting to look at 3 different section cuts, and they're shown here, the CP distribution over the chord lengths. And again, here we show in black this time the reference solution and the very strong shock at this locations here. And then POD combined with interpolation is giving you the green line here. And you can see that upstream of the shock, we have a way too strong increase of way too strong decrease of pressure. And also we have step function built into the prediction, which is very typical of POD because it's a linear subspace method. However, the ISOMAP method is capable of predicting the shock location and the shock strength pretty well, because it's only trying to use data which has to do with the prediction. Zooming in a little bit into the shock location, you can see this much more clear, right? The shock is well predicted in terms of strength and location. And we can then also plug this solution into the solver, right? So we're trying to now also optimize the pod coefficients rather than interpolate them by plugging the solution into the flow solver, minimize residual by varying the POD coefficients, and then you can further improve the solution. This is shown here, right? You're getting an even better prediction in terms of the shock strength and location with the same with the same ISOMAP snapshots. You can do the same, of course, with POD. I skipped the runtime here. This is just to show you building the model is rather cheap. Making a prediction with both ISOMAP and POD is even cheaper. And compared to a full order CFD solution, this is on the order of 4 orders of magnitudes cheaper. All right, next example is we are of course also interested not only in changing flow parameters such as Mach and alpha, we're also interested in changing the geometry, right, to arrive at some optimization capability. So here I have a full 3D aircraft configuration, and we are looking at the wing, and we are twisting the wing, so kind of we're at different section cuts, we're twisting the wing to find the best twist distribution, which is aerodynamically very important to get good performance. And there are 5 different sections where we are changing the twist. And then the idea is to build a reduced order model for the aerodynamics due to these geometry variations at, again, a transonic Mach number, which is our favorite hobby, to predict transonic flows. Again, we're trying to compare PUD and ISOMAP here. And this time, we are adaptively sampling the snapshots based on the ISOMAP embedding. Right? So this is also an interesting idea. Just go back one slide, maybe. So if you have computed this embedding, right, you can also look at where are the largest holes in this embedding, right? And the idea here is to compute additional snapshots
or right one?
Hello? Hello? No.
Ah, yeah, it's okay.
One, two.
Can you hear me?
Can you hear me? Good.
So, Bert, I think you need no introduction, no?
Okay. So, welcome back. I hope you have had a good coffee break. So this morning we had a fantastic talk of Stefan, and we learned about a real application, machine learning in real industrial application. So, and we also learned about reduced order modeling, control theory, and so on. So what is missing is what do we do if we want to control a complex, nonlinear, high-dimensional system like turbulence, and we have, say, 10 actuators, 10 sensors, and what should be our strategies for optimizing a control goal? And this is what I will talk about today, and I will use my usual path. So first I will come from human understanding, so model-based control, and then I will go to completely self-learning control. And we will learn from the wisdom of the eagle, which Steve has already introduced. So essentially we will try to imitate a bit the nature's way of learning. And this is based on collaborative work with Guy, sitting over there, with Nang, Luc, François, Van de Wey, Yuzhou, and again, Marek, Steve, and Ulrika. So first, I will introduce you to the applications of turbulence control. Then I will demonstrate you in one example benefits of feedback control. I will show you in the next example how far you can go with model-based control, high lift configuration with a two-frequency dynamic. And then we will go learn a new method, machine learning control, which conquers the nonlinear jungle, and we apply to distributed actuation in a turbulent jet, and a couple of other things. And for those of you who do not have experiments, but CFD, I will offer a poor man's version, cluster-based control, with a corresponding example. My lecture will end with a summary and with a quick demonstration of our machine learning control package, which you can download from the web page. Motivation. So we have seen already some nice motivation this morning. Another motivation is car control strategies for drag reduction. So if you want to reduce the drag for lowering the fuel consumption and so on, the first choice which you would take is aerodynamic design. So here you see a car, a concept car of Renault, obviously very aerodynamically designed. Where can you see that? What is aerodynamic about the car? Yes, good. What else? Well, look at the wheels. It has very small gaps. So this is one thing. Look at the bottom. It has a diffuser. So the wake is reduced. And now the question is, what could we do more on this car to reduce the drag even further? Well, we can build some actuators at the trailing edge over there. Is there a pointer? Any pointer? Okay. So we could make some actuation here at this trailing edge. We could blow, or we could suck, or we could do multi-frequency forcing. Here we can do it blindly, but of course the best is if we include the flow state, so if we do some closed loop control. So this is where we have the largest opportunities. And actually, a lot of these things have been done. If you go to a magazine called Research and Development in 2004, you see this car, and you see here the simulation with an experiment with actuation off, So the wake has a certain shape. So now you have zero net mass flux blowing here. There's a change in the wake structures. What is most important, you gain something like 20% drag reduction at 90 kilometers per hour. This translates to about 1 liter of fuel savings on 100 kilometer, and they claim it only took 10 watts of actuation energy. Sounds very good, but then we should see it at the cars, right? If it's that good. Any idea why we don't see it on the cars? But the answer is the solution is too expensive. So they've figured out it would cost the customer something like 3,000 euros, and none of the customers would invest this for these savings. Now there are a myriad of other applications. You have seen these examples already in Steve's talk. You can go from simple academic configurations to more practical ones, trains, cars, wind turbines, engines, and so on. So there are myriad of possibility of doing turbulence control and doing closed loop control. At the end, you will always have a dynamical system. So your plant, you want to reduce the cost. For instance, the drag, you have some perturbations into the physical system. So this is called real-world conditions. And you never know the full flow state. You only have some sensors, and you have to use the sensor knowledge to build a controller, and the controller drives the actuators. And there are several possibilities now. You can do open-loop forcing. Very famous is periodic forcing. This is very frequently used. You can do closed-loop control with sensor feedback, or you can do a combination of both. And you have seen this slide already, so I will give you more reasons to get inspired by this path, by the machine learning path. I want to show today that you can actually do the control optimization in the plant where you would not be able to do it with a model-based paradigm. So, Stefan, I'm sorry, I explained it already in my first talk. So now we benefits of closed-loop control. In my first lecture, we have discussed the wake stabilization with a hot wire sensor here and a volume force here, and the controller was derived by some model, so by some three-dimensional model. And if you want to stabilize a flow, of course, you need feedback. You cannot stabilize a flow without feedback. Now the question is, isn't this a bit academic? What do you do in the experiment? Well, here we have an experiment. D-shaped body flows from left to right. The goal is to reduce the drag. You have a couple of 15 pressure gauges. You can blow and suck on both actuators independently. Reynolds number is around 40,000, so it's reasonably turbulent. And I'm reporting now about a PhD thesis which has been done some time ago by Marc Pastor. So the question is, how do we design the control from the sensor readings to the actuation? If we don't actuate, we find von Karman vortex shedding. This is a smoke visualization here. Here you see a vortex, and a vortex, these structures should not surprise you. If you have a vortex is a low pressure region, so the fluid particles spiral around, and in order to compensate for the centripetal force, you need a lower pressure inside. So if the vortex is close to the body, low pressure, and you get an extra drag. So one control strategy is to prevent the vortex shedding here and delay it. Now the question is, how can you possibly do this? One thing is, if you look at the vortex here, it's anti-symmetric, so the U prime in this direction corresponds to the opposite U prime here. So maybe you should do symmetric forcing. And obviously the flow likes the harmonic frequency, so you should do something else. So you could take, for instance, golden section times the natural frequency to be maximally incommensurate. And it turns out this is a pretty good choice. Of course, you learn it in hindsight. So if you actuate with a frequency which is slightly lower than the natural frequency, then the flow stabilizes, and you get 40% increase in the base pressure, 20% decrease in the drag. So now you could say, I'm very happy with this open loop forcing. Where is the problem? Well, suppose, for instance, you would change the velocity a bit. Suppose, for instance, you would now decrease the velocity. Suddenly your actuation frequency, your physical actuation frequency becomes your natural frequency, and the drag increases again. So you have no robustness against change of your oncoming velocity. And so this is one of the reasons why we may want to use feedback. So in the next step, we do feedback control, phase control, something which is similar to what Scott was teaching. And now we get the same drag reduction, but now for all Reynolds numbers. So we can change the Reynolds numbers, and we still get this 20% drag reduction, and we also save on the actuation energy, 40% actuation energy. So now with every watt which we invest in the actuation energy, we gain 5 watts in the towing power. So this is energy, very energy efficient. By the way, you can also stabilize the wake with high frequency forcing, but then your energy investment would be significantly larger. Now there's one application where you cannot do anything with open loop control. Suppose, for instance, one of the actuators fails. You can only actuate on the lower side. So in this case, I can tell you open loop control will not work, and you need to do some type of closed loop control. You get the same drag reduction, the same energy, and again, this is not doable open loop. So this is a motivation why feedback maybe how feedback is beneficial for instance, a wake stabilization. So you came here also for some math, some equations. How can you treat these things on a more physics-based way? Well, you would typically start with a velocity field corresponding to the steady solution, and then you have a fluctuation. The fluctuation is harmonic. That means it can be spent by something like a cosine mode and a sine mode, so essentially two-dimensional approximation should be reasonably good enough. So we have seen now enough example of this case. The linear dynamic looks something like this. So these mode amplitudes behave like a growing oscillator, and you can actuate, and we can change, rotate the mode in such a way that we only affect the second oscillator. So this is single input control here. Now, how can we simplify things? We can now write things in polar coordinate and look at the growth rate, the natural growth rate corresponding with the linear dynamics, and you will quickly figure out this corresponds to that. And what does actuation do? The actuation is an extra term. So this one is a instability. So this one will always lead to the growth. So now you have to design your actuation in such a way that this is negative. How can it be negative? Very easy. If A2 is positive, then B must be negative. If A2 is negative, then B must be positive, and so on. So essentially, the sign of B should be opposite to A2. What we want to stabilize the dynamics, so we want to make sure that it decays exponentially fast. So essentially what we want, our controlled dynamics, controlled stabilized dynamics corresponds to this dynamics here. And now we would like to get a controller for this purpose. So a naive choice is the following. You take this equation here and invert it and solve it for B. Where's the problem? You divide by A2, and suddenly you get infinite control. Obviously, this is not a good choice. But you can go do something simpler. You can make the ansatz B equals, you make a linear ansatz with opposite sign. And now you can determine the gain such that the equation is satisfied in a one-period averaged sense. and then you arrive at such a controller. You see here, if the more you want to stabilize, the larger the gain. The more unstable the flow, the larger the gain. The more effective the physical gain of the actuator, the smaller the gain. So this controller makes perfect sense. What I'm showing you here is called energy-based control, and the advantage is I've taught you this now in 3 minutes, so you don't need to go through the control theory textbooks. This is one advantage. So it's a very simple approach. There's another advantage, namely, since it's an energy-based approach, it also works for nonlinear settings. So we have used it for most of our approaches. So this is linear full state feedback. Here you see an example. So we choose some parameter, growth rate 0.1, frequency 1, gain equals 1. So the story is always like this. If a coefficient is not necessary, set it to 0. If it's supposed to be small, set it to 0.1. So G equals 1. And if we want a controlled growth rate which is opposite to the natural growth rate, then this implies that the gain should be 0.4. I could explain why, but I will not do so in the moment. In the dashed line, you see how things spiral outward, and at some point, control kicks in, and now we spiral inward again. Control designed, finished. And you see it's a bit elliptic. Why is it elliptic? Because essentially you can only act in this direction. So when you are here, you have a strong gain, so you can significantly reduce the amplitude. If you are here, you can do nothing because your control has to be 0. So now we have a perfect understanding of linear control and a very simple method of doing so. Why is this of relevance for turbulence? So this is linear control theory. We have heard the exquisite talk of Scott. So there are a number of nice things you can do in addition, which energy-based control does not deliver. So you can guarantee optimality of the control, guarantee robustness. You can do state of the estimation from sensors, sensor-based control, and so on. So lots of nice things. Why is this in my lecture about turbulence control? Well, you have oscillatory coherent structures. You can have a dynamical model, a calibrated dynamical model for those. And at the end, you will always arrive at some phasor control for the dynamical system. So your control will always be the measured phase minus a difference, and then cosine, and then some gain. And you could also use empirical identification of the phasor going. At the end, you only have 2 parameters in your controller. To some extent, you don't need the model. So the model comes as an ornament to your publication or to your understanding, however you see it. We have also talked about nonlinearity. So there is one nonlinearity associated with Reynolds stress. The average flow does not stay as a steady solution. You move away. So we have seen it in my first talk. Now you decompose the velocity field in the steady solution, in the first harmonics, and in the mean field deformation. Again, first harmonics, mean field deformation. You get such a dynamical systems, which we have discussed earlier. So there is an oscillation where the growth rate is determined by A3. So A3 is the shift mode, it's a base flow variation, and this is proportional to the Reynolds stress. And so effectively, you have a locally linear dynamics which you can control. It will not surprise you that the control design works. Let's look at one solution. There's a periodic solution to this system, which is shown here. In weakly nonlinear stability theory, you say the growth rate is proportional to the Reynolds number difference to the critical Reynolds number. So the further you go away from the critical Reynolds number, the larger the growth rate. And at the end, you arrive at the Landau equations, which we did already in our first lecture. So you get a linear growth rate, cubic damping term, And in this setting, the growth rate is proportional to Reynolds number minus Reynolds crit, assuming a supercritical Hopf bifurcation, which you observe for the cylinder wake. So typically, you can relax this. So this is not really necessary. You can identify also a model even at high Reynolds numbers. I just mention it for completeness because there are a number of publications who do similar approximations from a stability perspective. So how can we design the control? Very easy. We do the energy-based control. Then we get something like this. We get practically the same controller, except that the growth rate now is the natural growth rate minus the mean field bifurcation. So this arises if we take the local linear model. So this is a justification of the linear parameter varying control. And essentially what this equation says, if you are in the limit cycle, then this growth rate should be 0. That means your actuation should be lower. But if you want to go closer to the steady solution, then your gain must increase. Now there's a sweet spot. At some point you have stabilized the flow, and then also this A2 goes to 0. So initially you have to ramp up your control, and then you have to decrease your control to 0 after stabilization. So this is the situation again. So now A1, A2, we live on the mean field paraboloid, which we have seen already now a number of times. You spiral outwards. At the end, you end up on a limit cycle. And then we do our control. You see the red curve here. And then we move downwards back to the limit cycle. If you want, you can try these type of things. So control design is easy. Modeling is also easy. Again, why am I teaching it? Well, there are oscillatory coherent structures. The base flow modulation on the mean field have been frequently experimentally observed, and what we found in our collaborative research center for flow control, if you don't take into account the base flow variation, then your control may not work. So this is a critical enabler for control, and which is also increasingly realized in JFM publications. And we also can identify the mean field paraboloid from experimental data from turbulent flows, where you would not initially expect them. Good. Now we go to another configuration, closer to what Stefan was teaching, high lift configuration. So this is a old-fashioned design, 3 sleds. We want to increase the lift. For this, we can do blowing and suction here at this point. Our plant is a MK epsilon model, and we do a 2D unsteady runs, structured grids, and so on. The purpose of this exercise is to explain why high-frequency forcing mitigates or increases the lift and also reduces the drag. So this is reduced order modeling for understanding, which at a later time we also use for control. If you look at the unforced flow, you see these type of streamlines here. So there's some vortices. If you average, one vortex here persists. Of course, this is not good. And if you look now at the fluctuation, you see heavy vortex shedding here. This is not good. So I've flown once in a Lockheed 1011, and when it was landing, high lift configuration, I could really feel the vibration. So this must have happened there. If you do some periodic forcing with a frequency which is 80% larger, then you get a much more streamlined configuration. In the average, this is just a small fluctuation, and the fluctuation which remains is high frequency shear layer structures, which you see here. So here this gives rise to a 15% lift increase, and we would like to have a dynamical model explaining this. We have now 2 states. So there's one limit cycle corresponding to natural shedding, which we can resolve with the POD modes without actuation. There's another limit cycle with the actuated flows. So these are 2 other POD modes which we use. The total fluctuation now has 4 POD modes, which you see here. And the base flow somehow has to respond to the strengths here and the strengths here. And as I will explain in a second, each of these Reynolds stresses from this fluctuation and this fluctuation changes the base flow. So we get two additional shift modes or two additional modes describing the base flow variation. So here you can have a forced transient from this limit cycle here or natural transient back. And this shall be described as such a dynamical system. And the fluctuation drives the base flow. So we derive the base flow effectively from the Reynolds equation. And the actuation is modeled essentially by the blowing and the suction here and the derivative. The reason is the following. We want to have a cosine and sine signal, and we never know to which phase our actuation communicates. So this is a model at which we arrive with some mean field consideration. I ask you to believe it for a moment. So this is what you arrive if you do harmonic balances. If you look at the first, if you look at the harmonics, contribution of the harmonics of the natural shedding and actuated shedding, what you see here, a dynamical system with two oscillators, one oscillator here, one oscillator here, and the actuation on this side, and the actuation only affects the shear layer structures. And without forcing, this growth rate is positive, so vortex shedding will always want to occur. The shear layer vortices are always negative, so without forcing you would not see them. So you have a damped oscillator here, which you need to excite, and you have a forced oscillator, an unstable oscillator here, which you cannot directly affect, but somehow they seem to be communicating. How are they communicating? If you look at the growth rates here, you find that the growth rate of the unstable fluctuation has a positive value here. Then there is a component which gives rise to the cubic damping. So without actuation, this growth rate will go to 0 by this amplitude increasing. But if you actuate strong enough, you also mitigate the growth rate. So if this term is as large as the growth rate, then this growth rate becomes 0, and von Karman vortex shedding cannot exist. Of course, the frequency depend on both energy levels, the other growth rates, and so on. But this is the key equation which you need to keep in mind. And what this equation tells you, you excite one frequency, it changes the base flow, and by changing the base flow, it mitigates the linear system of the vortex shedding. This is an example of frequency crosstalk, which you would miss with any linearized approach. Any questions so far? Good. So this is a model. Of course, now I have to show you that the model is not only a fantasy. What we do, we fit our model to the U-Runs data here, A1, A2 from vortex shedding, A3, A4 from the shear layer structures. And we see here two transients. So there's one transient going from the limit cycle to the fixed point, and then one from the fixed point to the limit cycle. So one is a forced transient, and the other one is a natural transient. And here you have the opposite scenario. You start at the fixed point, then you go on the limit cycle under actuation. If you stop actuation, you go inwards. And this is what our model does. And considering the simplicity of our model, this is already pretty impressive reproduction. There's one parameter which is extremely important. How does A3, so one of the modes, correlate with the actuation? So if you get the phase relationships wrong, of course, your model will have to be poor. The dashed line corresponds to the model, and the solid line here corresponds to the original runs data. Now we look at the lift, and when we turn the lift coefficient over the time, we turn the actuation on, and the lift increases. We see already the high frequency signature here. Then we stop actuation, and then it goes down, and then we see the fluctuation of von Karman vortex shedding. If we fit the lift coefficient with some expansion, we get a reasonably good reproduction. The dashed lines are what the model predicts, and the solid lines are what the runs predict. So what did we learn? Well, we learned a general lesson. And what we would like to do, we have the mean flow with a vortex. We would like to shift it into the direction of the potential flow. Unfortunately, we cannot do it. So what we are now doing, we have to play with the natural dynamics. We just use another fluctuation to change the base flow via a changed Reynolds stresses. So we go somewhere close to the base flow. And since we cannot control the von Karman vortex structures directly, we support the enemy of our enemy. And this is a strategy. So often you cannot kill the structures which you want to kill. I can give you many examples of this, but it's always easy to excite a structure. And then you have to excite the right structures, so the enemy of your enemy. And what are the implications of control? Well, let's look at our two oscillator models, so we call it generalized mean field model again, and we put in some numbers, so it's always the small quantities are 0.1. First frequency is 1, and we have high frequency forcing, so we call it 10. And we just look at one growth rate, so this growth rate is positive, damped here. Now, what we would like to do, we would like to mitigate the fluctuation energy von Karman vortex shedding and penalize our actuation. And the first idea which comes to mind, okay, let's do linear control. Let's linearize. If you linearize, you get 1.01. So these terms are missing. So the second oscillator is stable. Your control does not need to do anything, and the first oscillator cannot be affected. And that means linear control, the first oscillator is uncontrollable in linear control. You can only control it if you understand a bit of the nonlinearity. And of course, you know what you need to do. You need to excite the second oscillator above a certain threshold, 0.1, to have a negative growth rate here. So this is your understanding, which you have to bring in order to make control approaches work. Good. So the general approach, just a recap. You have a steady solution, base flow deformation, a component from unsteady vortex shedding from your actuation. So these are the two frequencies. First frequency, second frequency, you always need two modes. Each of the contribution has one corresponding shift mode, Reynolds stress contribution. So you always end up with 6 modes. And you can show that the general structure of the dynamics derived from harmonic balances and so on looks something like that. So we have, I will not go into much detail. You can now do the control design. You only have to focus on the growth rate of the first oscillator, which we have seen already earlier. You can do energy-based control, so you can make the ansatz B. You want to destabilize the second oscillator, so that you can make this ansatz, and you can say the fluctuation level has to be on a certain level. So you can want to identify this function as F, and you can do so from energy-based control. Long story short, I have identified this in a thing for the D-shaped body, where we have another frequency, and we have applied a corresponding control scheme, and it has worked reasonably well. Now, for the dynamical system, what we have here, without forcing, this is the first oscillator, A1, A2, A5. So you have the limit cycle here. On the second oscillator, you are at 0. Now, the transient from the steady solution here to the limit cycle, you start your actuation, you spiral backwards, and here you spiral outwards on the limit cycle, and this oscillator kills that oscillator, and you can see it more directly if you look at the two shift modes. So A5 is the amplitude associated with the first oscillator, and A6 is the amplitude associated with the unstable oscillator. So what you are doing here, you start here, natural shedding, and then you ramp up the fluctuation energy in the first, and have a certain change in the shift mode. You go up here, then you stop actuation, and then you go somewhere here. So this is what you get from your dynamical system. Why are we talking this? There are many examples which fall in this category. So there's high frequency forcing, which Ari Glaser is frequently talking about. There's low frequency forcing and so on. They can all be described in this framework. So one was a D-shaped body, high lift configuration, and I could add many more examples here. So the mechanisms which we have learned now for stabilizing an instability may be encapsulated in this model here. We have one component von Karman vortex shedding, another component could be low or high frequency shedding, and we have a base flow variation. Some forcing may be able to directly communicate with the first oscillator, and then we have to do phasor control. So what we have seen in the first example or in the numerical example. In some strategy we cannot do this, then we have to excite the second oscillator. So we have to use some open loop frequency crosstalk to kill the first oscillator. So it's a destabilizing control using frequency crosstalk. And what I did not discuss, because it's so easy, what you can also do, you can blow the instability away. So you can take, for instance, the D-shaped body, you can make your core undersurfaces there, you simply blow, and you blow the wake away, and you prevent vortex shedding. So in terms of the model, this would correspond for changing the mean flow, and thereby the unstable dynamic becomes a stable dynamic. So these are several strategies of taming an instability. Now there are many more things. So if you look in the literature, you find constant forcing, periodic forcing, opposition control. So we have seen it for the turbulent boundary layer, phase and frequency crosstalk. So this is essentially implicit. You typically have single input, single output. This is the effective mechanism. But there are many opportunities for multiple input, multiple output control. For instance, it's often found that if you use multiple frequencies, it's better than using a single frequency. How are you going to optimize those? Then at some point you may be curious. Okay, you have you do not only want to have multi-frequency, but you also want to have some sensor signal. Maybe you also want to incorporate noise. So this is a general idea of a controller which you get from the literature. And the next thing is maybe you want an automatic identification of the frequency crosstalk mechanism, automatic actuator selection, automatic sensor selection. So this looks like a big fantasy which can never be realized in any practical terms, but it turns out the solution is amazingly simple. And this is what I will talk now. Other questions so far? There were not, let's say 6 modes, yes. Well, you can take the first 2 modes are POD, the second 2 modes are POD, and the other, the shift modes need to be identified in a different method. These are empirical modes, yes, and they are effectively a POD mode if you look at the right transient, if you process them in the right way. Good question. So from your experience. So this is the starting point.
So maybe a bit in the same line. In other configurations, how much? I mean, you will also need to reuse your experience. This is okay, it's a way, but let's say you control a completely different problem. I don't know, a liquid film flow or something completely different. So you have to restart from your experience.
You have to restart from there, but normally you think you have another flow, and essentially your old experience becomes invalid. But if you find that if you excite one frequency, and you change another frequency. So if you have these frequency crosstalk mechanisms, and if you believe that the dynamics is linear quadratic, it needs to satisfy these equations. So this is, I would claim, a general property of linear quadratic dynamics, which have a self-amplified, amplitude-limited natural dynamic, which is killed by an excitation of a stable high frequency or low frequency dynamics. So it's a dynamical problem. It's not a physical problem. Well, you look at the Navier-Stokes equation. Can you answer me the question for the Navier-Stokes equation?
I'm talking more about the reduced order model that you built, right?
Well, you can derive the reduced order model. What? You look at the Navier-Stokes equation. So which terms do you have? You have the viscous term. So the viscous term is, of course, linear. You have nu Laplace u. Now you look at the convection term. So if you take the base flow and the fluctuation u0 u prime, it's linear. It has to be in the linear term. Now you look at the other linear term, so u prime u0, so nabla u prime u0. It's also a linear term. So there's a linear part of the convection term, which also goes into the linear term. And then there is a residual part, so nabla u prime u prime. Essentially, if you average this would be the Reynolds stress. So this part goes into the quadratic term. And so if you look at the pressure equation, so then you have the pressure-Poisson equation. It also has a linear and quadratic term. It turns out the quadratic term is something which you can almost always neglect. So the pressure term typically only changes the linear part. And you, as mentioned, you can derive everything what I've shown you now is Navier-Stokes consistent. So the slaving is your Reynolds equation. And the other equation is your equation for u prime. Thanks for letting me make this point. So we have now seen an example of model-based control. And maybe I've convinced you that under some conditions, you can derive a model for your plant. Typically, if you have 1, 2, perhaps 3 frequencies, but would you be optimistic if I tell you you have broadband turbulence, if you have a turbulent jet? Would you try to build a model which you use for control under these cases? Well, if you do runs, then essentially you kill all the dynamics, and you cannot do control anymore. If you yes, but U-runs, what can you resolve with U-runs? You cannot resolve, say, different frequencies, shear layer growth, and so on. With U-runs, you typically only, the survivor of a U-runs is typically an oscillation. Typically, you get a periodic solution, and you don't get a U-run solution which shows you broadband spectrum. If you get that, then you're not doing U-runs anymore.
No, but I mean, you're using U-runs to get your Reynolds stresses. I mean, what you are doing is you are exciting Reynolds stresses in your wake to kill the wake. That's what.
Yes, right. And there are 2 ways. So for instance, so one thing, you use a fluctuation as your agent, and the fluctuation changes the base flow via the Reynolds stress. And the next thing is if you do constant forcing, then you change the base flow directly. So this is the brute force killing of the instability, and you can change the base flow directly, or you can use the Reynolds stress as your agent. And at the end, you typically live on a manifold, the manifold which is determined by the Reynolds equation. So we have seen this model-based control, which may be associated with Norbert Wiener. And we have seen the movie of the eagle doing the amazing maneuver on the landing on a rock under gusty conditions. I have discussed already that we can, that this eagle does smart trial and error. Smart trial and error means you try a controller, you measure the performance, you try another controller, and so on. You hope to optimize things with some clever algorithm. So in case of the eagle, it means the death of many eagles and millions of lives of evolution. But you can do it in a way that no animals are harmed. And you use some other approach from the mathematics community. The cost function has typically two parts. So one part what you want to achieve, for instance, drag power reduction, and one part is your cost, which you have to take into account. So you typically want to minimize the cost. And what you typically want as an engineer, you want to minimize your cost regardless how. So you are not a priori interested in a model, you are interested in solving a regression problem, meaning finding a controller, let's say here a sensor feedback to the actuation, in such a way that it minimizes the cost. So this is a regression problem, but you see already it's a pretty tough regression problem. You have to see the effect of one function on the overall dynamics, and I would claim this is a variational problem. Control theory leads to a variational problem of the controller. And the question is, how can we solve it? So, of course, we don't want to take the Navier-Stokes equation or anything like that. So this is already difficult enough. Somewhere we need a data-based approach. And now we assume something. Let's start simple. Suppose we have one feedback control. Let's take the cylinder oscillation where we rotate. So now our B here is the rotation speed of the cylinder. And we measure, for instance, the lift and the lift derivative. Now we would like to find the parameters P1 and P2. Seems a simple problem. I will introduce you now to an algorithm which we will use and generalize later, so the genetic algorithm. So who of you knows the genetic algorithm? Okay, I would say maybe 30%. And who of you has used them already? Almost the same amount of people. Wow, good. Anybody wants to explain it? No. So what you are doing here, now you discretize your parameter in a kind of funny way. You say, I discretize my parameter in terms of 3 bits. There's a value here corresponding to the bit 0, 0, 0, 0, 0, 1, and so on, and 1, 1, 1. So you discretize your parameter in 8 bits, and the other one also in 8 bits, so that if you put these 3 bits together in a 6-bit thing, this characterizes your controller. And you now do you want to optimize your controller with these bits, and there's a technique which also emulates nature. First, you start with some generation and you use random bits. So these are your random controllers, your random parameters, typically of the order of 100. The next thing what you do is you determine the cost. So you test them in your experiment or in your simulations, and then you resort them in such a way that the good controllers are at the top and the bad controllers are at the bottom. In this evolutionary algorithm community, this is called, the controllers are called individuals. And then you want to create a new generation which is supposedly better, which finds better minima or climbs down a found minimum. The first thing what you do, you take your winner of the first generation and put it in the second generation. We probably agree that this is a smart thing to do. And then we apply some genetic operation which may create some new controllers. One operation is called selection. That means, or replication. You take one of the controllers and put them in the next generation with some probability. Why might this be useful? Well, this is your memory preservation. So you don't want to start from scratch. And the other thing, your chances of taking the first individual the first individuals have a higher chance of being selected than the worst individuals. So to some extent, this is your memory of your control landscape. Another operation is mutation. So what you take the controller, you take a random number of bits and you replace the bits with random other bits. So we probably agree that when you do a mutation, you find something new. So maybe you find a new minimum. So the mutation essentially does exploration for you. And there's another operation which your parents did with you, crossover. So you have some genes of your father and some genes of your mother. And which genes are here now randomly chosen? So I say, okay, these genes and these genes are now replaced. And the crossover tends to breed better individuals. It's not obvious from a mathematical perspective, but it's frequently found. And now you have your new generation. In the new generation, you test them in the experiment or in your simulation. You determine the cost, and you start again until some convergence criterion is reached. And it looks like, well, brute force trial and error. So when I saw these approaches the first time, I got stomach aches. So it took me several years of waiting before I would apply them anywhere. But it turns out they can be very efficient, as we will see later. Maybe a visual, why didn't we could have done a gradient search. So now we had two parameters. Nobody can prevent us to look at a slightly different parameter and slide down the gradient. If this is here our control landscape, so the performance with P1, P2, then the chances are big of sliding into local minima. So what you want to avoid with an evolutionary algorithm is you start with an army and you want to make sure that you, on the one hand, slide down the minima which you have identified and maybe find new minima which you would have missed with a gradient approach. And we have, I've shown you the evolutionary algorithm, something like genetic algorithm, for this one already in my first lecture. Now, we would, at the end, we would like to identify a controller. What is a controller? In the simplest case, the controller maps our sensor signals, maybe 10 sensor signals, in 10 actuation commands. And regardless which approach we are using, at the end, we have a finite number of operations. So maybe the exponential and the four basic operations. This is one thing. In the real realization, we have a finite number of variables which we can use. So this is our registers here. And we will always do a finite number of operations, so which are listed here. The controller now is coded in following way. So in the first, let's say in the first 3 registers, you put your sensor reading. You say your force register shall be interpreted as your control input, and then you may have a couple of constants. So this is how you may use the registers. Now you do a couple of operations. For instance, this is a random matrix. First you take register 5 and register 1 and do the subtraction. So you replace the first register with R5 minus R1. Then you do something with something similar with in the second operation. And the fourth you use the divided operation, and so on and so on. So now you do 5 operations. And if you do these 5 operations, first step, second step, and then the last step. In the last step, you have replaced the control signal 0 with something like that here. So this is the controller. This is something which you need to understand. And of course, it works also if you have 2 actuation inputs, 3 actuation inputs, and so on. So this is something which do you feel comfortable with that? To some extent, it's very simple. If I tell you the controller is a finite number of operations, which translates your sensor signal into your actuation command. The peculiarity here is that things are discretized in terms of a matrix. So you have an integer matrix. Now, what is a bit funny here is you have a finite number of control laws now, but it will explode. So let's take this. So you have roughly, let's say, six possibilities for each element. Let's say 5. So in the first row, you have 5 times 5 times 5 times 5 possibilities, and you have 5 instructions. So you multiply it, you take it to the power 5, so you get very quickly astronomical numbers. So you don't want to go through all possible controllers. You must find a smarter way. And probably, since I've shown you already the genetic algorithm, you will probably see, oh, maybe we can stack these things in some way and apply a genetic algorithm, right? So instead of zeros and 1, we have a finite number of elements here, and maybe we can do similar operations with this matrix. And actually, this is what we are doing, and the technique is called linear genetic programming. So here use the first generation with some random matrices sorted by performance. So this is the window. This is what you directly copy in the second generation. Now you do some, you randomly select some other elements for replication. Let's say you take the second one. Then you may do crossover with numbers 3 and 4. So crossover means you replace some lines with some other lines. Shown here. And another operation is you randomly take some integer values and replace it by random other integer values. So these are the same operations which you now use for your controller. So in principle, you are doing pretty much the same thing like in the genetic algorithm. So probably you are confident now that in principle, you can program this on a weekend yourself. And so what we are doing here, same thing. We typically test of the order of 100 individuals. Before, we had a probability which was larger for the first individuals than for the second. There's another way of realizing it, which is somewhat more convenient. It's called tournament. So what you take, you randomly select one of these individuals, you put them in the tournament, and then you take the best individual of the tournament. And so this way, the better individuals have a larger chance of being selected. And in the other case, you would have to assume a probability depending on the cost function, and this is a dangerous undertaking. So this tends to be more robust. But in principle, you do the same operations. You randomly choose the individuals, then you have your tournament. You randomly choose your operation, then you with random parameters and so on. This way, how you build the second generation, sort the individual, test them, sort them, and do it again until convergence criterion is reached. Now the question is, I've shown you already the example of this coupled oscillator or generalized mean field model, and you know already one solution which works. So the solution which works, excite this oscillator, make it humming all the time to kill the first one. Now we apply it with, I think, 100 individuals and 50 generations, and machine learning control has found a non-trivial solution. So the non-trivial solution is the following. What MLC said, do the following. When you are, so this is the first fluctuation amplitude. This is from the stable oscillator. This is your growth rate, and this is your actuation. So what machine learning does, actuate very hard initially. So make sure that fluctuation energy in the first oscillator is really high. And so this way the oscillator decays very quickly here. And then when essentially your opponent is dead, don't do anything. So then you can retire for a moment. And then now you have the natural growth, growth, until you have something like a level 10 to the minus 5, which is practically 0. But at this time, the control sets in, and it starts to be active again. knock out hard forcing, and then it does not do anything, and so on. If I now would ask you to write down analytically, probably none of you would have guessed this control solution, including me, at the beginning, number one. And if I would now ask you to write analytically the control law, which does this relay optimization. So you actuate until you are below a minimum level, and you stop your actuation when it's reached, and then you start again when a higher level has been reached. So probably most of you will have difficulties determining these type of controllers, but this tells you something about the complexity of the controllers, which you can find with such a simple algorithm. And it turns out it has surprised us many times in many dynamical systems, including fluid dynamical systems. So this is assuming this apparently stupid algorithm is much smarter than, for instance, me with 30 years of hard-earned experience. So this one was kept, and essentially what you are doing, this was not bang bang, but it was essentially a plus minus control. Yes.
But bang bang. I mean,
Yes, but for a short period of time.
That's something that you get from variation analysis. That's something
Of course, you can do that. Yes. But if I ask you now, would you have guessed that it is more economically to essentially bang hard and then stop and start again, and you build your controller B as a function of A? I think you would not have guessed the mechanism, and if I would now put you on the spot, so at the end of the lecture, you have to tell me the controller, not using any laptop and so on. You would not be able to give it to me.
That's something I had as a student. When I
so you work like me, yes.
I remember that as a student. I mean, there are many cases in which the optimum variational solution is bang bang. You go to the boundary, start, and then bang again.
My suggestion is you wait a bit, and I can give you many examples. First of all, this is not bang bang. This is just actuation on-off, and whether on-off is determined in a smart way. And if you wait, say something like 5 or 10 minutes, you will see completely different solutions, much more complex solutions. Good. So, who of you has seen already the fluidic pinball? Okay, 3. Means the rest has been asleep. No, I'm kidding. The fluidic pinball, essentially you actuate, here you can actuate the front cylinder, this cylinder, you can rotate them. We call it a pinball because essentially now you can determine the fluid particle comes here, you can rotate this cylinder and make it go here or make it go here. So you can essentially design the fluid particle path if you choose the three rotations. And this is just to give it a catchy name. You can also describe it as a cluster of rotating cylinders, but fluidic pinball is more fun. Now, what can you possibly do with these actuations to stabilize the flow? Any suggestions? So you have some vortex shedding behind, which you see here. So what can you do to stabilize? Yeah. Fast oscillation, good. The next is low oscillation, also good. High frequency oscillation, anything else? Well, you have learned phasor control, so phasor control should be on the list. What you probably are not thinking about at the moment, you can do a base bleeding, so by rotating them, you can create a jet here. You can also do core underforcing by rotating them in the other sense. You can redirect the flow. So there are a lot of possible. Most of the common drag reduction mechanisms or stabilizing mechanisms are here in this fluidic pinball. That's why we have chosen it. Mildly more interesting than a single cylinder. And the control problem is now the following. We measure, say, the V component here at this point, and we measure the U components here, and we would like to drive the cylinder rotations in such a way that we have an effective reduction of the drag. Xavier, so what control do we get?
Yes, I'll wait for a vortex to out the and then rotate the coanda for the.
So you would do coanda forcing?
Well, I'll rotate one of the cylinders to hit that vortex and then.
So you would do phasor control?
Probably.
Okay, good. So it's one part of the solution. So we are testing human intelligence now. So what we are doing as a control law now, we want to minimize the effective drag power. That means we also take into account the energy which we need for the actuation. And we have now a general control law which includes, for instance, constant forcing, which includes direct sensor feedback. So we have 15 sensors to our disposal. We take harmonic functions. So essentially we take the natural frequency, a golden section times the natural frequency, and we go with the powers of the golden section upwards to high frequencies and to low frequencies. So we have some kind of discretization. We can do something like broadband forcing if we want. What else can we possibly do? Okay, we can do the combination between sensor feedback and harmonic feedback. So this is something like this. But of course, if you look at our Max model and so on, you take into account the history. So our general controller looks something like this. It includes some harmonic forcing, and it also includes the history of the sensor signal, which is summarized in A. So this is a controller which we are now want to identify. And you probably agree this is a tough problem, right? Finding an optimum for that. So we do it 10 generations, 100 individuals later, we get something like 46% reduction of the effective drag power with a combination of, you mentioned it, one combination was phasor control, the other one is open loop forcing. So essentially you get so the front cylinder essentially responds with a phase to our sensor signal here. It selects one point. This is enough. And then you have a top cylinder and a bottom cylinder. You have some additional elements which reduce a drag even further. So this is something which you could not have guessed. And you also have an asymmetry here. You are in a slightly asymmetric case. And I could give you an argument why the control should not be symmetric, but it would be too far. It can be explained with Nang Deng's model. So this is a controller which you get and which you can identify with something like 1,000 individuals. So we have seen already the example from a previous lecture, Ahmed body, right? Now we go to jet mixing, and now it becomes very interesting. So you have a jet, flow goes from left to right. This is a contraction here. 6 actuators you can blow and stop to blow, so it's on-off actuation at this point. And what you would like to achieve, you would like to achieve a good mixing. How could you measure a good mixing? So one possibility is you look at the velocity, say, at the end of the potential core, 5 diameters downstream. If you essentially sense the jet velocity, what it means, no mixing has occurred, so the jet is immediately arriving at the sensor. If you have some good mixing here, then the velocity should decrease correspondingly, so this profile here should diffuse. Our control goal now is to reduce the jet velocity at this point, and this is the overall experimental setup, which we do not really need to know. Cost function, average velocity, we scale it, of course, with it. We had this scenario already, right?
No, yesterday.
So it will reboot automatically.
In the meantime, can you explain why genetic search is optimal in any sense, if it is optimal?
Well, I cannot prove that you get as a global optimum, but we can probably empirically quickly find out that it's always better than what has been proposed in the literature.
But just empirical. I mean, there is
Yes.
no theory why.
No, no
I mean,
theory. Yes.
I understand that you find a best optimum. I'm saying
Well,
that you
this
find
is
it
a goal.
quicker.
This is my goal. But at minimum, you find something reasonably good. You can never prove that you arrive at a global optimum. Now, there are some sanity checks which you can make. You can repeat essentially your experiments a number of times, and you can look at if you arrive at a similar controller. And this gives you the idea. Okay, so probably the solution which you find is reasonably robust.
No, I mean, I was not asking about the final solution, but the rate of convergence. Is it faster than, I don't know, just
Okay.
throwing pebbles?
I see your point. So there's no free lunch. There's one possibility. So you're on a Pareto curve. So one curve essentially is the complexity of the control which you want to consider. So we probably agree that the controller which we're considering here are much complexer than anything you would find in the JFM. So the complexity is large. And of course, for this type of complexity, you need to pay. And what you need to pay in terms of testing. And typically, so we have found most controllers in something between a few hundred to 1,000 individuals. So this is a minimum, in quotation mark, cost which you need to invest in order to get reasonably complex controllers. If you know already something about the control, if you want to tune one parameter, you know it's smooth and so on, of course, then you can have a faster learner. But then you restrict yourself to a subspace of the possible actuations. Empirical, everything empirical. There's no theory about anything in nonlinear dynamics, and particularly nonlinear control. Good. So we have sensor signal. So the sensor signal, we measure the velocity 5 diameters downstream. We also measure it in the shear layer. We look at the velocity. We look at the fluctuation. We take 9 different frequencies, which I don't want to explain. So essentially, our input are now 13 parameters, and our output are 6 parameters. The control output. So it's a reasonably complex law. If you just want to have a linear controller, you need 6 times 13 parameters already, and too much even for a simplex algorithm. So, surprise, surprise, we do machine learning control. This is the first generation with 100 individuals. This is essentially the performance which we measure in the first generation here. There is unforced flow, which you see here, which corresponds to a J value of 0.95. So the jet has only lost 5% of its velocity, 5 diameters downstream. Then in the first generation, it finds axisymmetric forcing with something like this performance. In the second generation, it finds helical forcing. In the fifth generation, it finds some flapping forcing. And then at some point, it finds some strange combined forcing, which is significantly better than the other ones. So essentially, now you are now combined. Effectively, it's a combination between helical forcing and flapping forcing. So at the end, things are converged after about 10 generations, 1,000 individual, and I want to realize the complexity of the controller which we have considered. Actuation, this is from the first generation. So here, blue means this is a time step. So there are 6 time intervals. This is one period. At the end, it turns out that periodic forcing, it always converts to periodic forcing. Then at some instant, all the actuators are on. The area is proportional to the time the actuator is on. If you see something thin, it means it blows for a short moment and strong. If you see something thick, it means it has been on most of this 1/6 of the period. So here you see axisymmetric forcing. In the second generation, you see flapping forcing. Here you see something like a structure which rotates helically. And then you see something which is more complex, and it requires some more arguments to convince you that this is a superimposition between combined and between helical forcing and flapping forcing. We did also some smoke visualization to corroborate our conclusions. I will not go in. I just want to make show you this is essentially the quick learning curve which we have. And now the question is, what area of the control landscape do we populate? So this is a proximity map. Again, if two controllers are close, so each point is a controller, that means they are very similar. If they're different, if they're far away, they are different. So here, essentially, you see the proximity map for the first generation. This means if you go to the right, this is good. If you blue here, this is bad. And first generation finds axisymmetric forcing, then it finds helical forcing, then it finds flapping forcing, and then it finds combined forcing. So looking at the proximity map gives you already an idea of your complexity of your state space. And there are techniques essentially to distill the topological features of this. Maybe at some point also interesting for you. So this is what we get at the end. And I can give you many more experiments. We have performed something like 24 experiments and 12 simulations and many dynamical systems and so on. We have always found controllers which has outperformed existing optimized control. It selects the sensors, it selects the actuators. There's small chances for model-based control. And in most of the cases, we have been surprised by the mechanism. So we did not anticipate the frequency or the mechanism the control was doing. So this is a big case for machine learning control. And I will give you a brief idea about cluster-based control. The question which you can ask now, okay, this is wonderful. You can do 1,000 simulation or 1,000 tests. What do you do in simulations? And this answers your questions. Suppose you have only your budget for 50 simulations. What should you do? Of course, you would not use this approach, but you can do something else. For instance, you can take your original database and you can take the natural flow and maybe some forced flow. The next thing what you are doing, you cluster your database. So at the end, you may arrive at something like 10 different centroids. Then you say for each of the centroids, I assume a certain actuation. So if you can blow a suck, then this is a single parameter that now your mapping from your flow to the actuation is characterized by 10 values, mainly the actuations at these 10 different centroids. The controller which you do is now a linear interpolation. So if you are here, you would interpolate somehow these values. But the key point you realize is you may have a high-dimensional function from your sensor signals or even from your flow to your actuation, but you coarse-grain it to a low-dimensional representation with centroids with clustering. And then the next thing what you do is very obvious. You take essentially the values on the centroids and you run a simplex algorithm on top of it, and you see if things are moving down. And I will show you an example. So here you have the wake behind the wing at a high angle of attack. There's some blowing which you can do at the front. The clustering gives rise to something like 10 clusters. These arrows indicate the transitions between this. I could explain these different flow features. I don't want to do it. I just want to say here, this is here low drag, this is high drag, and the lift is approximately constant. So we would like to shift things away from here to this one, and we do the cluster-based control with a simple simplex algorithm. And here you see 10 parameters. That means we have 11 vertices, and we choose them close to each other, and we get this type of performance. Now we do a simplex algorithm, and we run at it, and we get a cost, which is here. So essentially, it's the drag plus some actuation cost. I will not go to the detail. I will just say the drag has been reduced by 41%, and the lift has remained constant. So what we are essentially doing here, in some of the clusters, so in the low drag clusters, we suck. In the high drag clusters, we blow. This is a solution of cluster-based control. Now these bad clusters are not populated anymore, and we have achieved what we want to achieve. We have shifted the population from bad states to good states with a very simple control. So I'll leave it to you later to ask me details about this approach. Now, summary, we have discussed model-based control, and you see there's a beauty if you understand your control, but there's also a beauty if you automatically can identify your optimal controller and where you would have no chance with your understanding. And there is if you look at the modeling options, there are many more than we have discussed here. We have discussed some of these options. I invite you to read the review article with Steve. And you can also use machine learning not only for identifying the control, but also to identify your black box model and for many other purposes. At some point, we can go into the experiment, and after something like 100 runs, we know the optimal controller, we have a reduced order model, we have everything which provides us with a good solution and a model for understanding. And I hope I've convinced you that this is that's a machine learning approach, that's the inversion of the steps makes turbulence control student-proof, and that this is something, the first thing you should try. Just to save your time, and when you have found a good mechanism, you can invest in modeling. And from here on, I want to Miguel. I'm computationally impaired, so I asked Guy to show our XMLC package.
Hi, everyone.
So.
Okay, great. So here we are. I guess the main file has been already unzipped.
You need a microphone, probably.
Oh, yeah. I think it will be okay. Yeah, don't worry. Or maybe when I.
Let's make it perfect. Otherwise, you're the only one. No, you do it yourself.
Okay.
I may kill you. I will see you, Richard.
Maybe too much. Okay. Hopefully it's stable.
Okay.
Thanks.
Don't put it on the table. Put it in your pants.
Sure. How do I look? Is it okay already? Everyone can hear me?
Maybe use the other one.
Okay. I think it will be all right. So here's the main file. It's already been the main folder has been already been unzipped. So we have many files, many folders. They are all explained. The contents are explained in the README file. So just so it's been coded so you can use it on Octave on MATLAB if you don't have MATLAB. So you just have to work on the compatibility. So first you can go to the compatibility folder, sorry. And then you can run the adequate script. So in this case, Octave. Let's do it. If I can. On the Windows version, you just have to copy the files that are in the MATLAB Octave folder to the main folder. You just overwrite them, and it will work. So now we can go to the main folder, and then just run Octave. In this case. Okay, great. Wow.
This does machine learning control.
Now the first thing to do is to launch the initialization script to load all the paths necessary to create the MLC object that will be optimized. So here it creates also an MLC object that contains our problem, so XMLC. So the name of the run, Dynamical System Benchmark. The name of the run is important for saving. You can change it, for example, by so the name of the object is MLC. You can by default, you can create by your own. It's all explained in the README file. More details, I mean. So you can change the name, for example, for MLC.parameters.name with an uppercase, and then here, just put up. My run, for example. Name is changed. And now, if you want to see again the features, MLC.show problem, the name has changed. So the problem to solve is generalized mean field model. So the problem is in the here, the plant folder. Here you can add your own problem. So here's the generalized mean field model. So one file for the parameters. It will contain all the MLC parameters. You can look at it. And another file, the problem, which is actually our solver. Here another folder, my problem, that is a copy paste of the other one. You can modify it at will following your conveniences. So here have the number of inputs. One is going to control the the generators mean field model have two oscillators, one unstable, one stable. Want to bring the unstable one to the fixed point by actuating on the stable one. So if and we're going to actuate on one of the components of the stable oscillator. Number of outputs of the sensors, there are 4 for the 4 variables, A1, A2, A3, A4. So you have then some parameters, the population size, 10, and stem strategy, elitism. So we'll keep only the best individual from the last generation to the next generation. Crossover, 6%, mutation, 30%, and replications, 10%. So we're going just to show you the unactuated dynamics. Okay. Let me just clean this. Okay, we changed the size, but maybe I made too much. Yeah. Anyway, so here we'll take just the parameters of the parameters to modify them. Here we have I modify just the initial condition close to the fixed point for the unstable oscillator and far from it. So 0.01, 0, and 0.25, 0.25. Here just run the solver with 0 control law. This is the control law, so 0 for no control law, no actuation, I mean. So all parameters, A1 for the visualization. So let's just run it.
Will you smile from Alicia?
Yeah, sure. Okay, so we have also a plot option. So we have a plot. On the top right, left, sorry, you have the controller, 0. On the top right, yes, you have the growth rate of the unstable oscillator. So here for the phase portrait for the unstable oscillator, phase portrait of the stable oscillator. So we have our initial condition here is the red circle, here the other one. So we reach our limit cycle after we have our nonlinear saturation. And for the other one, we reach the fixed point. So we are going to use as the initial condition. We're going to use 1 point on the limit cycle and the other on the fixed point for the unstable oscillator. So I'm just going to run two generations of a population of 10 individuals, because on Octave the for loops aren't as optimized than in MATLAB. So it takes more time, and then I'll show you some other run I did earlier. So to run the optimization process, you just have to say mlc.go, and here indicate the number of generations you want. For example, 2. Let's go. So first of all, you have the populations will be generated. So this is the Monte Carlo step. We have candidate solutions generated randomly. It's optimized that new individuals are different from the other ones. Then we have the evaluation of the individuals, one by one, with the cost. Okay. Now, so no bad individuals to remove. It means that some of them can make the solver explode. So those will be excluded, and new individuals will be generated. In this case, it's okay. Then we have the second generation that has been created with the genetic operators. Sorry for the. Then it's going to be evaluated. So the first one is already done because it's the one that we got from elitism. We have the cost. Then there are other ones that are already done that those have been created with replication. So just copy paste from the last generation. So we don't need to evaluate them again. But of course, there's an option that you can force the re-evaluation if you had some problem with some noise. Okay, so now this is after 2 generations, this is the cost of the best individual. which is not that great, with some control law. If we can see it by the method mlc dot best individual without an s, and here you have some information and the plot. So this is not that great, well, but we only have 10 generations that evolve through, no, 10 individuals that evolve through 10 generations. So it was expected. So here just, so I have the cause, the control law. Yeah, that's it. So now I'm just going to show some other run I ran yesterday. So if you want to save your run and continue it later, you can do with the method mlc.save Octave for the Octave version, and then the MATLAB for the MATLAB version. You can also save Octave files from MATLAB, but not the other way around. So you can just exchange from the other. And that's all. Or just like this. Like in the save runs, it will create the MLC Octave save. So now we want to load this one that I ran earlier. So if you do mlc dot load, where is it? Octave, and here put the name of your run. Of course, you have to be careful with the names, with the naming, not to overwrite some other runs. Benchmark.
Benchmark.
Thanks. Here it is. Okay, great. This time we have 100 individuals. We can look at the best individual. You can see that the cost is much lower. So the unactuated cost is 0.1. So here is the solution. So I run the 100 individuals through 10 generations, so 1,000 evaluations. This is what we found. So I only run it on 25 periods. Sorry for the stable one is a bit under-resolved because it's much slower on Octave. But on MATLAB, it took around 1 hour to run the 1,000 evaluations. But on Octave, on MATLAB, it's around 10 minutes. So here you have like a force on strong actuation at the beginning. Then we reach a fixed point. And you can see that at the end we have it starts again to destabilize. Of course, we should run it on a larger time window to have a proper controller that sees what happens after the destabilization. Also, you can take a look at the whole individuals that have been explored with the mlc.convergence method. I take some time to create some pictures, some figures. There are some other methods you can find on the cheat sheet script. We are already there. Okay, so here we have a spectrogram of the control laws. Each column corresponds to one generation, and the color is the cost in a log scale. You can see through generations there is an increase of the of performances that takes the more and more the generation, the population. Here's one of them. Here's the distribution of the components of the cost function of yes. So JA and JB. Here have also Pareto diagram and the Pareto front of the controllers with the color map showing the generations. You can see that the red or orange individuals are on the lower bound of the Pareto front. You can like this. Here we have two other plots. Maybe this one is less interesting. And here are the distributions of the control loss through generations. So more or less the one that we saw with the jet mixing problem. Here with different colors for how the individuals have been generated. And the red line showing the best control law at each generation in the evaluation. And the green one for the median performance. And that's it. It's that easy.
So I told you which software I use for my solving problems, writing emails, and now you also know to whom you could write your emails if you're interested in machine learning control. Thank you very much. Great presentation.
Thank you. By the way, this software will be available in the folder of the chapter, okay, of the lecture series. So you will have it. You have a question there?
Hi, thank you. I just saw, just off of the top of my head, that there was a Monte Carlo part in the graph. In a sense of genetics, are you playing God with some of this stuff in order to cover more area in your parameter space?
Okay, good point. So somehow you have to initialize the first generation, right? So somehow you have to initialize your first generation.
Mm-hmm.
And the first generation is essentially Monte Carlo. You use random individuals.
Okay.
And now the hope with the genetic algorithm is that you become better than Monte Carlo, that you are actually learning something. If you look into the book, some people claim that that the genetic algorithm is not really better than Monte Carlo. So essentially, if you take 1,000 individuals propagated with genetic programming and 1,000 individuals with Monte Carlo, then they are almost equally good. But we have strong evidence that we are actually learning something and that we are populating the minima. So the first is Monte Carlo. This is the initialization, and from there on you propagate with genetic operations.
So, okay, what I'm really asking is, with the playing God thing, if the problem with genetic stuff is that you can basically not, unless you introduce a heavy mutation rate, you cannot spam stuff that is not in your initial parameters, right?
Of course you can.
Okay.
We are using control laws. At the moment you do a mutation, you can get arbitrary control laws. I mean, the dimension of your possible control laws is infinitely large.
Okay, but mutation is random, right?
Mutation is random, yes.
Oh, have you considered playing God and saying, okay, it might be a good idea to do my mutation in feasible directions, if you will?
I like this question. So essentially now you want to replace the genetic operation by something which is much smarter. And I would ask you, please wait 3 more months and then look in archive. So we can do something much faster without genetic programming.
Maybe I have also a very quick question. I agree with you that some of the problems that you've shown are extremely complicated from many perspectives, but they have also something that makes it relatively easy as compared to others, and it's the fact that you can afford the cost of being wrong. But how about cases where a mistake can put the system in the wrong trajectory? So in this case, is it a way to put in the cost function also the cost of being wrong?
This is a very practically relevant question, and several answers. So if you know in advance which range you would never like to probe, then do the pre-testing. In fact, what we are doing here, before we evaluate a cost function, we look with some criterion if this controller is completely ridiculous. For instance, it always gives values which are 10 to the 38 and so on. So one thing is, if you know in advance which range is bad, you would exclude it with pre-testing. So you take the individual out, you replace it with another individual, so that all the individuals which you are testing are sanitized. Then another strategy, what you are doing, you can do a bit gradient search. For instance, suppose you have a controller which works, and you don't want to make a radical test, for instance, combustion chambers. You don't want to explode a combustion chamber. This is very expensive and it can kill people. No fun. So what you can do now, essentially, you can identify a small variation of an existing controller, and now you can go in and you can use it more in the sense of a stochastic gradient search. So there are many ways how to be, in quotation marks, more careful and constraining your controllers.
Thank you. Other questions?
So by the way, another thing, so the actuators, when we have too high frequency components in our actuation, then suddenly the matrix valves don't work anymore. They're either on or off, so we want to avoid this. How do we avoid this? Very simple. So we have, after the controller, in quotation marks, another filter, which makes sure that the on phase or off phase has a minimum length. So our controller at the end is what the genetic programming suggests, and an additional post-processing which guarantees that we are not going over the limitations of our actuators.
Need to know them in advance.
Yes, right. So this is where your essentially engineering experience comes into play.
I have a quick question which sounds a bit silly, but anyway, I will ask it.
I like it.
So first of all, I would like to know how you estimate whether the system is controllable or observable beforehand, and secondly,
controllable?
Whether it's controllable or not with this kind of actuations, and whether it's observable or not with this kind of observations you use in your simulations. And second question is, to what extent this technique overperforms some methods like DPQ learning of policy gradient methods?
Good question. First of all, when you are talking about a controllability and observability, you are in a linear framework. And so by looking for nonlinear dynamics, essentially we play trial and error, and we do whatever is possible with a plant. So I would argue that if you would do linear control, then the observability and controllability space should match. You should do balanced truncation and so on. But all these type of approaches collapse at the moment of nonlinear dynamics. And the second question is very interesting because you are asking essentially, why did we choose genetic programming? So you go in the machine learning community, everybody hates genetic programming because it's so brute force, and COSA has alienated so many of the colleagues. There have been big disputes and so on. One reason is because it will work, I claim, much better than neural networks. And I can explain you why. With neural networks, you have a mapping from an input to an output, from a sensor signal to the actuation command. And now you have to, how do you train a neural network? Typically, you solve a regression problem of the first kind, a data fitting problem. So for a given input, you know already the output. So you train it, input, output, input, output. And at some point, you have an input which is close to your original input, and then you have your output. You have 1 million different coefficients, which you need to tune. Essentially, you would normally only use it for a regression problem of the first kind, data fitting. So this is why you are not using it. Now, control problem or closures is a regression problem of the second kind, a variational problem. So you have no notion of a local error. If I tell you, for these sensor signals, you do these actuations, you know nothing about the controller or the performance. And for these variational problems, you now have suddenly in a neural networks, maybe 1 million parameters to tune. How are you going to tune these 1 million parameters? Impossible. So I would claim the niche application of neural networks is fitting problems. For instance, you can nicely use them for modeling. If you have a dynamical system and you know for your state, your derivative of the state, wonderful, apply it. But if you have a variational problem, a control problem, or a closure problem for that case, then there are other techniques. And at this point, genetic programming is the most powerful tool which we have found.
Thank you. So I propose we go for lunch, and we come back more or less, let's say, at the same time as agreed. So 13:45. Let it be 13:50 max. Okay. Thank you.
about the paper Rabon, Mr. Noak.
You were thinking about what? He has an enormous knowledge. So he's one of the leading experts in reinforcement learning, one of the leading experts in neural networks, and combines them, and he has to fudge the problem a lot to make it somewhat work. So I'm in contact with him. We have joint publication, and he would never apply his approaches to our problems.
Okay, good to know. Thank you very much.
Well, it may be more successful
doing anything? Yeah.
Thank you very much.
Everything is okay? It works?
I think so. Yeah. I think that is.
Okay, so welcome back. I propose to start with the last lecture of the lecture series. It's going to be given by Professor Jimenez, who will give us a perspective on the future.
Okay, thank you. Can you hear me from the back? They don't complain. Okay. Okay, so thank you to the organizers for giving me the opportunity to be in the last one. So I guess my role in part is to try to decide whether these forces that have been unleashed during this week here are evil or benign. Okay. As you can see, I think they're benign. Okay, so the question is, I mean, you remember that in the first day I was speaking about coherent structures, and I told you there was going to be a second day, which is today. Speaking about whether we could consider computers as scientists. I mean, basically, the theme of the whole talk is going to be how much science can be automated, and I chose that because science is the easy part. I mean, one thing is to try to understand what is the next movie that you want to see in Netflix, but science is a well-constrained system in which there are rules, so we can see whether we are playing by the rules or not. Okay, so basically. Also, there is the question that you're any kind of engineer, you know that if science can be automated, it will be automated by somebody. And then the question is, you have to decide whether that means that computers could substitute you or me. Is probably too late, but you maybe, yes? Can you tell them? You can't hear me? Can you hear me now? Better? Okay. Okay. So, I mean, this was one of the slides that I used on the first day. It's the scientific method, is the way that science is supposed to work. You know, first you observe something, then you explain it, try to explain it, then you test it, and blah, 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 blah. You keep going around that, okay? And there is a bunch of smaller scale activities in there, which, you observe, you make observations, ask questions, gather information, blah, blah, blah. The question is how many of these things can be automated. And this is going to be the computer. This is going to be the woman that is going to try to substitute us. Okay? And the question is which of these things can be automated and which ones are not. Okay? I mean, some of them are obviously automatable or automatizable. I don't know how you say that. For example, make observations is what DNS has been doing for the last 40 years, okay? Gather information is also trivial. I mean, it's something that computers do that. They put it into a database, and then you have to do whatever you do with them. Make predictions is also a computer thing. Test predictions is also a computer thing. And then there are these things in blue, which are things that is not clear whether the computer can do for you or not. And this is what I'm going to try to apply to one example, and then see whether in that example the computer is doing any of these things, or these are things that are, at least at the moment, necessarily human. Okay. Now, why should we worry about this now? I mean, it's certainly not going to be happening tomorrow. Any of these things are not going to become computerized tomorrow, but maybe in 5 years, yes. So the moment is now to start thinking about them. And the first reason that we have to start thinking about that because computers are getting faster, and you all know that. You know that every 25 years, the computers increase by a factor of roughly 1 million, okay? Which usually has meant that we do things which are more complicated every 10 years, okay? From my point of view, what I do is I simulate turbulence. In the 1970s, I was doing something like this, 2D turbulence, okay? And then I started doing something like this, and then me or other people did things which are now fully developed three-dimensional turbulence, Okay? And this is one way of using faster computers. Okay? And when we do it that way, we know that there is somebody here, which is the one decided what to do and reading the analysis, which is us, is the thinker. They say the computers are not thinking, the computers are just computing things. Okay? There is a limit for that. I mean, there is the largest thing that you can compute is roughly what can be computed in the largest computer in the world in 3 months. That's basically a PhD thesis. I mean, 3 months is not a PhD thesis, but 3 months of computer time for the largest computer in the world is a PhD thesis. It will take a few years, okay, because you have to, you never get the whole machine. The machine, I mean, doesn't work. You have to write the software. You have to read it. So this is the limit of things that can be done. And on top of that is us trying to interpret things, okay? But here there is another line, which is the line of 10 seconds, okay? And the thing is, this line is 25 years away. 10 seconds is roughly 1 million times faster than 3 months, okay? So when 25 years have passed, what used to take 3 months now takes 10 seconds. And that changes things a lot, okay? For example, this thing that I could do in 3 months in 1970, 20 years ago, I could do it in 10 seconds. Then it was free, okay? This thing that I could do in the 1990s, now it can be done also in 10 seconds. Then it's free, basically, okay? And that means that thinking is beginning to change, okay? The things that were being analyzed by us here now can be downloaded up to a point to the computer, okay? Because you think of yourself, we try to think of ourselves as very intelligent things, but we are machines at the end. I mean, there is nothing not machine-like about us. We are just machines that do something, I mean, quite fast. And now computers are beginning to do them as fast as us, okay? And that is changing things, okay? The second thing that has been changing all this time is, of course, artificial intelligence. We have been speaking here about machine learning, artificial intelligence, and I told you the first day that that can be classified into things. It's either symbolic or sub-symbolic. The symbolic is the classical kind of artificial intelligence in which there is a thinker, us, who makes hypotheses and then creates rules from the hypothesis, embeds those rules into an expert system, and then runs it again. Something like what you were saying this morning. I like that, okay? I like the physics part, okay? But this is the old artificial intelligence. As I told you, people were doing this in the 1970s, and then the thing crashed for a while and then came back and blah, blah, blah. And now, of course, there is this new artificial intelligence, which is the sub-symbolic part. And the sub-symbolic part works differently, okay? You don't start with a hypothesis. You start with a sample, with a lot of samples, okay? You create algorithms, okay? And this is done by something that is not an expert system. It's a neural network, a self-organizing map, whatever, okay? The difference between this and that is that here we learn, and here the system learns, okay? It's a basic difference. I mean, here you don't really know what has happened. The system knows what has happened, but that's up to him or her or whatever. I don't know what a system is, okay? And if we forget this part of the artificial intelligence, what happens is that we don't learn, okay? And there are two possible outcomes to this. We can decide not to learn, to completely outsource our thinking to something else, okay? Or we can try to learn what the system has learned, open the box, okay? And there is a huge branch, I can tell you, there's a huge branch. You look for this acronym in the web. This is called explainable artificial intelligence. And there is a big community on that, because there are other reasons why people want to know how the computer works. I mean, I might want to know how the computer works, what the computer has done, because I don't want to be left behind. There is a lot of lawyers that want to know what the computer is doing in case something goes wrong, in case the plane explodes or something like that, whose fault it is, okay? It's because the computer didn't think correctly, because the programmer didn't think correctly, because there was a cosmic ray that just downed the plane or whatever. So there is this is something that is important. And it's something that I think that we should always try to do that. I mean, don't try to apply a neural network unless you have a way of opening it and looking inside. Okay. So, question. I mean, let's now try to start looking at these questions now. Okay. Now that we know that the opportunities is that the computers are faster and they are thinking in a way that is basically different from us. Okay. What are these things can be automatized? Can we ask the computer to ask questions? Do they frame hypotheses? Can they judge those hypotheses? Okay. And I'll give you this example. I want to go through this example, which is something I've been playing with for the last year or so, last 2 years maybe. The thing is, I, the thinker, put a meta question. I mean, the meta question is not a specific question. I want to know about this, okay? And in this case, I want to know about 2D turbulence, okay? 2D turbulence, there are several reasons why you can choose that. First is easy. It's one of the things that can be computed for free, okay? And then I think I know, or the community tends to think that they know how it works. So if the computer gets conclusions, I can second guess the computer, okay? Say, okay, well, what you have done is right, or what you have done is wrong, or what you have done is new. That will be fantastic, of course, okay? So the idea is, what I want to know is I have a two-dimensional field. I run it for a while, and then the field has changed. I want to know why. I mean, and basically, I am a control-minded person. If I want this to be different, what do we have to do here? Do we have to touch that vortex there? What you're seeing here is vorticity. Do you want to touch that vortex there? Do you want to touch that vortex sheet in there? I mean, what do you want to do? I mean, what things here are important for what happens later? Okay, this is going to be my meta question. Okay, and then how do I do that? Well, there is several things that I can do for that. The first thing is I want to define what is important, what is a relevant feature. Okay, and a relevant feature is something I'm going to define it like something like this. You break this initial field into pieces or into subsets or something. You do something to one subset, run the two systems for a while, see whether something has changed or not. Okay? If it has changed, that piece was relevant. If nothing has changed, that piece was not relevant for this particular question, of course. Okay? And there are things. I mean, the first thing that you have to check is whether they are relevant and irrelevant things, where some things are more relevant, some pieces of the flow are more relevant, some pieces of the flow are less relevant. And then there is a lot of things that you have to, or that you can decide for that. What to do to that piece, how long to run, okay? And these are things that unless you know the answer, they have to be tested, okay? At the end of today, well, at the end of this first part of the talk, you're going to be seeing something which is a couple of million runs of this. But a couple of million runs of this took 10 days, okay? So it's not terrible. It's something that can be done, okay? And in those couple of million runs, you test many things. I mean, the idea is to test many things. And here I give you two examples, okay? In this case, I'm doing an experiment in which I take a piece of the flow, you break the flow into this grid in there. You take one piece of the grid, and then put the vorticity in this piece of the grid, put it equal to 0, okay? And then run it, okay? This is what happens when you don't do anything, and the flow goes from this to that, okay? This is what happens when you zero this part of the flow here. And then, as you can see, basically nothing has happened. This thing was not important. This thing was not relevant for this particular perturbation. Doing this particular perturbation on the flow didn't do anything interesting, because you see, I mean, this vortex here is that vortex there, that vortex there is still that vortex there. Essentially, very little has changed after a while. Okay. In this one here, this one turned out to be important. Okay, you zero the vorticity there, and then this vortex is not there. Now has become round. I mean, this thing is also different. There is a big hole here that was not there. this thing was important. And it is important to notice something. I could not have guessed that this thing was important. It was important that this thing was not. It's something that has to be tested. I mean, it's not that I went there and killed that vortex. No, I zero the vorticity here in a place where basically there is no vorticity. I zero it there in a place which was whether originally there was not vorticity either, but this one turned to be sensitive, and this one turned to be insensitive. So these are things that you have to test. So you test them. I mean, you test them, and then also make sure that something has happened. I mean, that there is a real difference between one case and the other. Not in this big norm of the flow looks different, but in the details of what has happened to the perturbation that you have put in there. This is another case, but this is basically the same idea. The perturbation that I am putting here is not zeroing the vorticity. It's just changing the sign of the vorticity within that little piece. Okay, and then this tends to be an irrelevant set. I mean, this little box in there tends to be not sensitive to what I'm doing. And you see what happens here initially. This is the difference between the perturbed and the unperturbed flow. Then you run it for a while, and you see that, okay, well, it moves a little and then decays. Okay, if you do this for one cell that turns out to be sensitive, then it's something completely different. You change it here, okay, and then the thing rearranges the whole flow. This is the difference between the two flows. So the fact that you have blues and yellows there means that it's not that you are destroying vortices that are moving. So the thing that was here now is there. Okay, so the whole flow has changed, and it has changed because this perturbation has turned out to be important. And looking at what you have done, looking a posteriori at what you have done, you can almost understand what has happened. You see here in both cases, I'm changing the vorticity, and the two cells have a lot of vorticity. Actually, they were chosen. They were chosen by me a posteriori just to do the slide, so that both of them, the initial magnitude of the perturbation was the same, but the final was very different. And then you see here the vorticity was strong, but it had different signs. Okay, so I changed it, and then nothing happened because those two signs are going to cancel each other. Okay, while here it was basically all of the same sign. So if I change it, then I'm changing something. Okay, so now you have to test these things. Okay, you have to let the computer search around. Okay, and how do you do that? Well, the way I'm doing here, you take the flow, change it into a subset, and you test whether these subsets are important or not. You do this for all subsets. You label these subsets. Okay, you say this thing was important, this thing was not, this thing was important, blah blah blah. Okay. You repeat it for many initial conditions. You typically run this. This is not the way. This is just for the slides. Typically, I break that into a grid that is somewhat finer than this. Then you repeat this maybe 1,000 times or something like that. Do statistics, okay? And basically, the statistics that you do is you create a label training set. What I am doing is I am classifying the flow into cats and dogs. Okay, this is a cat, this is a dog, this is a cat, this is a dog. And now you launch one of these discriminators to discriminate between cats and dogs. Okay, what is that make a cat a cat? What is that makes a dog a dog? Okay, and this is the nest. This is how you do your set. I mean, there will be many of these subsets. Each of them with a relevance ranking. Okay, this is high, this is low, blah, blah, blah. And you have to test this for different times. Of course, you don't know over which time you have to test these things. And then for each of them, you store some properties, okay? Because what you want to know later is which is the properties of a cat that makes a cat, which is the property of a dog that makes a dog. And in this case, for each of these subsets, I am storing the entropy within the cell, the rate of strain, the magnitude of the rate of strain, and the kinetic energy within the box and shows these three, okay? So now on top of that, you launch a classifier. A classifier in this sense is something that for a particular property, for example, for the entropy, tries to decide whether there is a threshold for the entropy in which all the relevant things are to one side and all the irrelevant things are to the other side. And in 1D, you can do this by hand. Otherwise, you use something that is called a support vector machine, which is a classifier that you can get in MATLAB or in something like that, okay? It's basically, it's like a cluster, but it's not a K cluster. I think it's for classifying is much better than K clustering. It just looks at the, here looks at the border. It doesn't care if there are many things here and many things there. It just looks at where to put this threshold in such a way that a minimum number of samples are misclassified, okay? This is how it just adjusts the thing like that, okay? And then you get here something which is classification efficiency, which is essentially how many samples are classified correctly, okay? In this case here, which is for this particular initial perturbation, and for this particular variable, 98% of the samples were classified correctly. In this case here, which corresponds to the thing here, roughly half of the things are misclassified, which means it's as good as chance, okay? So this is a relevant diagnostic variable for this experiment, okay? And this is an irrelevant diagnostic variable for this experiment, okay? Now, what do we have up to now? Well, what are these? My understanding of this is that these are questions by the computer, okay? The computer is not making a smart question, but it's making questions. It's asking questions. It's asking questions to the flow. What happens if I do this and then choose this variable? Well, then I get this answer, okay? So these are the questions. These are the computer theories, okay? Now, you have for these questions, and then you try to explain which of these things make sense or not. You say, well, this variable is important, okay? The computer theory, the outcome of this is that the computer now has a theory of the flow. The things which are important for two-dimensional turbulence are vortices, okay? Now, this is one possibility. There are others. There is no reason. You have to do more experiments. You have to choose more variables. It's not clear that for all the experiments that you do, the theory that you have is the same. And actually, they are not. There are two possible theories that my particular experiments have found, okay? These are two experiments. In which case I was playing with the vorticity of the cell. In the other case, I was playing with the velocity of the cell, okay? In the case in which I was playing with the vorticity, then, not surprisingly, the computer found that the relevant quantity was the total entropy in that cell. In the case in which I was playing with the velocity, not surprisingly, the kinetic energy was the important thing. Whenever the kinetic energy was high, that thing was sensitive to experiment with the vorticity, with the velocity. Whenever the entropy was high, this thing was sensitive to playing with the vorticity. That was not always true. There are cases in which you do something with the velocity and you end up with the result that the vorticity is important. And then you could sit down and say, okay, why, okay? Or you can let the computer do a little more for you, okay? And do a little more for you is, okay, now I have my set, my training set, okay? And I say, well, I know for this training set, I know which things are important, and I know which things are important because the vorticity is high, or because the energy is high, or something like that. But that's good for the computer. The computer goes there and tests for the vorticity. That's not good for me. I really want to know more about the structure. I want to be able to do physics with that, okay? And the vorticity is an extensive quantity. It's an intensive quantity. I want to know what else do all the cells that have something that are important, what do they have in common? So you let the computer build a template for you. And a template is basically a conditional flow field around things which are important from the point of view of the vorticity, from the point of view of the velocity. For example, these are two cells, these are these two cells here that I know are important from the point of view of the kinetic energy. Okay, they're important for a particular experiment, which is the experiment in which I change the sign of the velocity in that cell. Okay, and then I say, okay, how do the flow look around that? Okay, and then you essentially build a conditional average, and this is something like a POD, but you cannot do a POD with this because of the invariances. Okay, this flow is invariant to rotation, is invariant to reflection. You can change the sign of the vorticity, and the flow will still work. So you have to, for each of these cells, you have to create a set of actually 8 cells in which this flow rotated by 90 degrees, 180 to 270, and the same thing flipped right to left. And then for each of these set of things, you choose the one that looks more like the first one, for example, and you add them and do an average. And you create something which is a dipole. A dipole for me was a surprise. I mean, I was not expecting dipoles. I was raised on the idea that two-dimensional turbulence is a gas of vortices, it's a set of vortices. That was the idea that everybody had in the 1980s, okay? And dipoles, of course, I mean, people knew that they were dipoles, but they were not considered important. Apparently, they're important, okay? You see there are two. I mean, in all the experiments that I have done, I have only ever found vortices or dipoles, okay? And a vortex looks like a vortex, and a dipole looks like a dipole. You see two vortices that have a jet, and this is where the kinetic energy is, okay? As I tell you, in the 90s, in the 80s and the 90s, there was a bunch of people doing 2D turbulence. That was the thing to do at the time, because it was possible to compute. 3D turbulence tended to be expensive, okay? And then the idea was, and this guy, Montgomery and McWilliams, I mean, they essentially got the idea that 2D turbulence could be explained like a bunch of vortices, okay? I mean, 2D turbulence is not a completely artificial flow. It's what happens in the ocean. It's what happens in stratified flows, or is close to what happens in stratified flows. Geophysical people like 2D turbulence because it really looks like something like that what is important for a rotating flow, okay? And this is what you get. This is a vortex, and this is a vortex dipole. So this is okay. Now, what are the dipoles? Well, dipoles were known to happen. I mean, even if this same guy, 6 years before, I think that this is wrong. It was not Montgomery, it was McWilliams. But okay, a guy in there, okay? Notice that there were dipoles, said, okay, well, these dipoles form and then decay and nothing happens to it. Well, apparently, something happens to them, okay? They even had a name. They were called modons, okay? And they're supposed to be the thing that gets blocked in the North Atlantic and blocks the weather in Europe for a couple of months, okay? So now we have two theories. It is important that whenever you get this, you have to validate your theories, okay? And I mean, validation means several things. At some point, you have to validate your statistics are okay, of course. And at other point, you have to make sure that what you are doing has something to do with the flow, not something to do with your experiment. Not only, something to do with your experiment, okay? And this way of doing that is, for example, something that we have found up to now is that when you look at pieces of the flow which are important for the flow, they look like these templates, either a vortex or a dipole, depending on which experiment are you doing. You want to test the converse. whenever you see something that is a vortex or a dipole, are they important or not, okay? And what I have been showing to you now is these statistics for the most relevant sets, okay? These things which are more relevant, and they look, the error between the template and the flow is not very large, okay? So this is okay. Now, you do the same thing for all the, for all the pieces of the flow. And then discover that this, yes, is true. I mean, when the thing doesn't look like a template, this error between the template and the flow is large, then the thing is not relevant. Whenever you have something that looks like a template, this thing is relevant. Of course, I mean, this has a width. I mean, this is, I mean, all these experiments are basically Bayesian physics. I mean, you're looking at what is more probable when you do this. I mean, it's not a rule. It's a statistical rule. Almost everything in turbulence, you end up with a statistical rule. Okay, and this is true for the vortices in the case in which vortices are important. This is true for the dipoles in the case with the dipoles are important. The important thing is these black things in here. The red part is what happens for the most relevant thing. I mean, you are just seeing the tip of that PDF there. Okay. Of course, then you have to do the basic test that you are not doing artifacts. Okay, or a basic test that always has to be done. You have to test against your training set. You have, I mean, to make the difference between testing against your training set, testing out of your training set, and these are these two lines here. The thing which is solid are for things which are being tested against the training set. The things which are dashed are things which are being tested outside of the training set, and you see that they agree. So in this case, things are okay. Okay. What else? Okay, we have a theory. We have the computer making some questions. I don't know whether they're interesting or not, but these are all the questions that I made the computer look at them. Okay, I tried to be stupid. I tried to be as stupid as possible, which is not hard. Okay, I tried not to tell the computer what to look at. I just said, okay, well, do this, do that, do that, do that. Okay, and then let the computer classify the output by itself. Okay, I was trying to not guide the computer too much because I know a lot about the physics of this flow. I tried not to put that knowledge into the computer, and the computer came out with these two pieces of ideas. You either have vortices which are important, or have dipoles which are important. Okay. And then the question is, well, do you really see vortices and dipoles in the flow? Actually, not really. I mean, this is Platonic turbulence. Okay, this is the Platonic idea of what is in the flow, but you don't see round vortices. What you see are things like that. Okay, and actually you can see that because this axis that I had there in the previous slide is the magnitude of the error of the difference between the template and the actual flow divided by the magnitude of the template. Is the percentage error or the fractional error with respect to the template. And you see that these things are quite high, of the order of 1. The error is of the same order as the template. Actually, the two things which are unrelated will be of the order of square root of 2, so it will be here. So, but still, this thing is large. And you look at the flow, and it's true. I mean, there is very few things that look like a round thing in there. Okay, but still, I mean, let's say, well, now that I know, or that I think that I know that vortices are important, or dipoles are important, can I go at the flow and look at how many vortices do I have, how many dipoles do I have, how many pairs do I have? So, I mean, what you take is, you take the flow, segment it in some way. I mean, there are, you find some way, some reasonable way of segmenting it into positive and negative regions of vorticity, okay, not vortices, but regions of vorticity, you get things like that, okay, and then decide, okay, well, these things will have something nearby, and let's try to make dipoles to see whether they're dipoles or not. To do that, you sit in a vortex here, find another vortex of roughly the same size. I mean, it will not make sense to try to pair this little vortex to that big one. but yes, maybe this one with that one, and see whether the closest one is something of the same sign or of a different sign, okay? And then you create a bunch of possible pairings of the vorticity, and you find out that actually most of the vortices are forming dipoles, okay? Forming something that look like dipoles. I mean, so this discovery, I mean, this basically this unexpected result of the computer, it actually found something that was there. Okay? So this is as far as the experiment goes. I mean, I'm not going to be speaking too much about this experiment anymore. What I'm going to try to do now is analyze what have we done. Okay, what has happened here? Okay, how much, how true is it that we have convinced the computer to think or not? Okay, so there are several questions. Okay, one thing is how expensive it is. Okay, can we do this for a flow that is not two-dimensional turbulence, that flow that is really an interesting flow? The other question is, have we discovered something about turbulence? Okay, have we really discovered something and something new? And then have we discovered something about data processing? Okay. The first thing, cost. I mean, as I told you, this is not very expensive. I mean, you have seen basically 2 million simulations of two-dimensional turbulence in 256 square, each of them in a old processor of one of the classes that I have in my basement. Takes 10 seconds. That means that this basically is 200 processors a day, okay? 200 processors a day. Each node has 12 processors, so this is basically 20 processors, 20 node days. That means it is a week, okay? The total computer time spent in this is something like a week, okay? The actual clock time, I mean, which is the time it took me and the group I was talking to do this is something like a year, but most of the year was spent talking about what to do. Okay, this is one of the things that you have to learn more, but then doing the thing is free, basically. Okay. Now the question is, can you do this for for a more interesting flow? Something that we are doing now. I mean, this is just not being done by me anymore. It's done by a postdoc. Okay, and she's doing 3D turbulence in 256 cube. Okay, this begins to be something. I mean, I thought I knew the answer for 2D turbulence. I don't know the answer for 3D turbulence. I don't know what is important. What do you have to change in 3D turbulence so that the turbulence changes? Okay, I don't know for how long I have to wait. These are things that now have to be found. Okay, this is not 10 seconds, but in a GPU, it's like 2 minutes. Okay, it's actually less than 2 minutes. This is what it takes. I mean, the GPUs that we have are Titans, and you put this this will fit in a single card, and it will run in like 2 minutes. And you probably have to run as many simulations as before, maybe a little less because now we know better what to do. Okay, and that is going to take. Actually, most of this has run already, like 100 cluster days, okay? Assuming that the cluster has eight GPUs, which is what it has, my particular cluster, no? Okay, so this is still something that can be done. I mean, it's not impossible. These are the sort of things that can already be done in a small lab like mine. It's not like a big company. It's not like DLR or something like that. It's something that can be done at home, okay? Later I will show you an example with a channel, which has already been done also, okay? I don't know how long it will take us to think about it, but it will probably be, but it better be less than 1 year because she has to leave, okay? But now, so this is the cost. The cost is okay. Have you learned anything? I mean, up to all these things. I mean, have you learned something about turbulence? Really, not much. And the reason that we didn't learn too much is because I think there was not much to learn. I mean, I on purpose chose a problem in which I knew the answer because I wanted to look at the answer of the computer and check whether the computer had made some terrible mistake or not. Okay, so not really nothing new, but the dipoles were almost new. I mean, when I saw the dipoles, Actually, at the beginning, I told you there was something there which papers are written on this. And on the first 2 papers, I missed the dipoles completely. I was not expecting dipoles. I was expecting vortices, and I found the vortices. It was only after letting the computer play a little more that the dipoles came up. So it was that basically there was a computer discovery. Okay, it was not a completely new discovery because as I told you, dipoles were known. Okay, but they were never considered to be important. Okay, something that the relevance of the dipoles to two-dimensional turbulence is something that came out of this exercise. Okay, and then something that I think is very important is for one of the first time in turbulence that I can remember, we are really looking at causes. I mean, not correlation, but causes, causation. We are really saying, when I do this, this is going to happen. Okay? There's a difference between, as we all know from detective movies, correlation is not causation. Okay? Correlation is when I see something happening, I tell you when this thing happens, this is going to happen. Causation is if this happens, this is going to happen. It's different. I mean, correlation is something that has been there. The typical example of correlation, which has nothing to do with cause and effect, is day and night. I mean, days are correlated with nights. You see a day, 12 hours later there is a night, but has not. I mean, certainly by changing the day, you are not going to change the night. I mean, by putting a parasol, you are not going to change the night later. Okay, this is a correlation thing that happened. Another thing that you are probably very used to is LES modeling. LES models is you somehow have decided that whenever you see a rate of strain tensor which is S, okay, then the stress tensor can be approximated by that formula there. It doesn't tell you that this is the source of that. It just tells you that there is a correlation between one and the other. Okay, structures, all the things that I was showing you the first day. I tell you when you see something like this is a burst that contains Reynolds stresses. I'm not really saying that burst is the cause of the Reynolds stresses. I'm more or less saying that burst is the container of the Reynolds stresses. When you have seen, when you have one, you have the other, but that's not the cause. Okay, correlation is actually has nothing to do with physics in a sense. Correlation is the science of prediction. I mean, you see this happening, you say, well, this is probably going to happen, but you don't know why. Okay. If you remember this distinction between symbolic and subsymbolic intelligence, correlation is basically subsymbolic. It's what happens when you do a linear fit. You pass a linear fit, okay, or a nonlinear fit, or a complicated theory, but you're just describing the world, okay, and you're using that to predict something. Causes are different, okay. Causes are you're really saying if this thing happens, this is going to happen, okay. If this thing doesn't happen, probably this thing will not happen, or it will happen differently. Okay, this is something that implies a flow of probability from one place to the other. Okay, and it depends on time, and that is very important to realize, because otherwise you get lost into all sorts of chicken and egg arguments. Okay, which is the cost of the chicken. Okay, something like that. Well, the cost of the chicken probably makes no sense. The cost of the chicken depends on which time you're looking at. The cost of the chicken over 20 days is the egg. The cost of the chicken over 40 days is another chicken. Okay, and then there is nothing wrong with that. I mean, it just the way it's a description of what happens. It's really a cost. It doesn't make sense. This other question, which is the ultimate cost, that question probably makes no sense. Okay, it's a meaningless question. There is no cost at infinity. Okay, there is no ultimate cost. There is, I mean, you're interested in these things. There is a very nice essay by Bertrand Russell that you can find in the internet, because it's an absurd journal or something in 1912, discussing which is the meaning of causation, which at that time was involved with the idea of God and all sorts of unholy things that you don't want to enter, okay? But the idea is that, I mean, it doesn't make sense to speak about causes in absolute, but it makes sense to speak about causes with a particular time, time horizon, okay? You decide, okay, I want to know what happens at turnover, before now, and then there is a cause for that, okay? For example, I mean, in this case, this particular cell here was the cause of that, okay? After a time which was 5 turnovers, okay? And we had to try whether it was 1 turnover or 5. We really tried. We really made a long simulations and essentially look at when this thing got lost, and it got lost. I mean, the time it takes for the effect of the causes in something like turbulence has to do with the Lyapunov exponent. I mean, when you are much longer than the inverse of your large-scale Lyapunov exponent, the thing stops making sense. But there is a time in which there are causes and which are effect. In the same way that correlation with the science of description or the science of prediction, the causation is the science of control. If you want to control something, you really want to know the cause. Okay? So this is something that can be done. I mean, the computer has been able to do that. Okay? Essentially, you say, okay, all of these 3 things, have been doing well. Several of these things have been filled by the computer. The first one is the questions. I don't know how to make a computer make intelligent questions, but this computer was able to make questions, okay? The thing is that because it's cheap and it can make many questions, you can let the computer make many stupid questions on the hope that some of them make sense, okay? But it's something that can be done already, okay? So this part we can more or less outsource to the computer. We can move ourselves out of that picture. Probably not completely, but in principle we could, okay? We can also try to make the computer look for the hypothesis. Basically, that is a classification problem, okay? You do the experiments, you ask many questions, you see the answers, and say, now you say, okay, well, put those answers together into a corpus, okay? That is a classification problem, okay? And that can also be done by the computer. In this case, it was done at this stage, okay? This is the computer theory. The computer theory was, well, for this particular experiment, this explains what has happened. There's another stage of this, which is, okay, well, now the computer knows this, please explain it to us, okay? And these were the templates in there. This is a very important part of this process. I mean, this is the process in which you go from sub-symbolic to symbolic. This is the process in which you go from the computer learns to now you learn, okay? And this has happened in this case, this has happened there, okay? And then there is the final question. I mean, we have automated the questioning. We have automated the thinking. Now, can we automate the judgment? Probably not. If anybody has an idea how to do this, I will be very happy to know about that. But I really don't know how to let the computer decide whether this theory that was proposed by the computer is interesting or not, okay? And the problem is not that the theory is not bad. The theory explains things. It's the question of whether it's interesting or not. And the question of whether it's interesting or not has more to do with me or with people than with the physics, okay? This is something that we don't really know what it means to have an interesting theory. We don't know what is. I like to put this not from the point of view of interest, but from the point of view of beauty. We need beautiful theories. It's not something that is supposed to have been said by Einstein. If he didn't say it, he should have, because his theories were beautiful, okay? And this is something that we have to decide. We can decide by ourselves if we are interested in knowing the answer. Otherwise, probably there is a way of letting the computer follow this cycle until it converges into something. But it might not interest us at all, okay? We might not want to know about it. I mean, what do you care, okay? But if we want to to decide whether this explanation is interesting or not is something that we have to decide by ourselves. So in this first part of the scientific cycle, okay, I think that the role of people will start to decay for a while. Okay, the computer can do it faster than us. Okay, here I think we are still important, probably not because of the physics, but because of us. Okay, that is a danger. I put a danger signal there because up to now, I mean, I told you in the discussion of the first day, my interest is in the inhuman part of artificial intelligence. Okay, what can the computer tell us that we cannot tell? I mean, anything that I did here could be done by any of you in much less time than a year ago, because it's fairly easy. Okay, but I'm interested in the part that was not clear. I like the dipoles because they were not predicted. I mean, I didn't know about it, or I had forgotten about them. Okay, and this came out of this, and by just breaking the cycle here with me, that is a danger signal. It's a signal that might spoil the whole exercise. Okay. This, by the way, this is what I call Monte Carlo science. Okay, this is basically of doing science by searching, tap, 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 and maybe genetic science. I don't know, but essentially searching randomly. Okay, okay, and this is not the first time it has been tried. I mean, this has been essentially what you need for this is to have a way of exploring the universe which is fast enough that you can afford it. Okay, and the first people that were able to do this were the biochemists. Okay, and they do this routinely. The first paper that had in the name RoboScientist, it was this paper in like 10 years ago. Okay, and it was this machine, and it was called ADAM, of course. Okay, okay, and apparently what it was design drugs. Okay, they were designing proteins to be good for some particular sickness or something. They were trying to solve something, okay? And essentially because the biologists by then knew how to play with DNA and knew how to create DNA and then transform that DNA into proteins, they were able to, I mean, this thing was able to stay in a room trying new things for a long time, and apparently they found something, okay? Found enough for them to build another bigger machine some years later that was obviously called Eve, okay? And that apparently is still working. I saw a paper recently in which not only, I mean, there was not a, I mean, these papers came from a lab in Scotland, okay? The paper that I read was from a company in California. They were not only doing this to design something, the machine was reading the literature for hints, okay? Was reading the literature, understanding the literature, find which possible molecules were going to be good for cystic fibrosis or something like that, and then designing this randomly, okay? So this is something that has been done already, and it's industrial right now, okay? I told you that I was going to tell you something about channel. This is a paper that is still in archive from the Carlos III, okay? And it was done by Flores and Pastor. Basically, they are doing a channel. I told you, causation is the science of control. They are trying to control the drug in a channel, okay? And basically, they are doing the same thing. They have the channel, the flow is going this way, and then near one of the walls, they have a volume force in which they either push up or put down, okay? For a short period and for a small volume, okay? Do it at random and then try to find which are the places in which this thing is doing something good, okay? So they just do many experiments and then collect all the places in which the drug is decreasing and then look which are the characteristics